Human sensory perception operates within astonishingly narrow bands compared to the full spectrum of physical phenomena pervading the universe. Vision detects electromagnetic radiation between wavelengths 380 to 700 nanometers, the visible spectrum from violet to red representing merely 0.0035% of the electromagnetic spectrum, extending from kilometer-wavelength radio waves to 10 to the -153 TH gamma rays. Hearing registers air pressure oscillations between 20 and 20,000 Hertz, missing infrasound below 20 Hertz produced by earthquakes and elephants, and ultrasound above 20,000 Hertz used by bats and dolphins. Touch, smell, and taste similarly operate within limited ranges, determined by receptor biology. Mechanoreceptors respond to pressures exceeding threshold force. Olfactory receptors bind specific molecular shapes from thousands of possible volatile compounds, and taste receptors detect 5 basic categories among infinite chemical possibilities. This sensory bandwidth, honed by evolution to detect survival-relevant stimuli in ancestral environments, defines the reality accessible to unaided human perception. The electromagnetic spectrum spans at least 24 orders of magnitude, from extremely low-frequency radio waves, with wavelengths measured in thousands of kilometers, down to gamma rays, with wavelengths smaller than atomic nuclei at 10 femtometers. Between these extremes lie radio, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays, each revealing different aspects of physical reality, invisible to others. Radio waves penetrate dust and reveal cold molecular gas in galaxies. Microwaves include the cosmic microwave background at 2.7 Kelvin, remnant radiation from the Big Bang. Infrared radiation betrays heat signatures from warm objects, including stars, obscured by dust. Ultraviolet light ionizes atoms and reveals hot stellar atmospheres. X-rays emanate from million-degree plasmas in galaxy clusters and matter spiraling into black holes. Gamma rays mark the most violent processes: supernova explosions, gamma-ray bursts, matter, antimatter, annihilation. Each wavelength band discloses phenomena completely invisible at other wavelengths, demonstrating that reality contains vastly more information than any single detection method can access. Other organisms perceive reality differently through sensory systems tuned to their ecological niches. Dogs hear frequencies from 40 to 60,000 Hertz, detecting ultrasonic rodent vocalizations inaudible to humans. Bees see ultraviolet light between 300 and 650 nanometers, perceiving patterns on flowers invisible to us, guiding pollination through UV nectar guides. Pit vipers possess infrared sensing pit organs, detecting thermal radiation from warm-blooded prey in complete darkness. Sharks sense electric fields through ampullae of Lorenzini, detecting bioelectric signals from hidden prey buried in sand. Mantis shrimp have 12 to 16 types of color receptors compared to humans' 3, perceiving polarization and potentially seeing spectral distinctions we cannot imagine. Migrating birds detect Earth's magnetic field through cryptochrome proteins in their eyes, navigating using geomagnetic information completely inaccessible to human senses. Each species inhabits its own perceptual reality, its Umwelt. In German biologist Jakob von Uexküll's terminology, an organism-specific slice of physical reality determined by its sensory capabilities and neural processing. Sensory bandwidth, the range and resolution of detectable stimuli, fundamentally determines perceived reality. Bandwidth isn't merely sensitivity, but information capacity. Number of distinguishable states times detection rate. Human vision distinguishes roughly 10 million colors at 60 frames per second across 180-degree field, with approximately 6 million cone photoreceptors per eye. Yielding information rate approaching 10 megabits per second. But this represents only photons between 380 and 700 nanometers, missing 99.9965% of the electromagnetic spectrum. Hearing processes 20 to 20,000 Hertz sound at roughly 30,000 distinguishable pitches times amplitude resolution, yielding perhaps 100 kilobits per second, missing infrasound and ultrasound. Total human sensory bandwidth is estimated at 11 million bits per second across all senses, yet conscious awareness processes only 40 to 50 bits per second. The vast majority of sensory input is unconsciously filtered, with consciousness experiencing minuscule fraction of available information even within our limited bandwidth. Reality, even as perceived by our senses, vastly exceeds conscious experience. Defining reality becomes problematic when acknowledging these limitations. One definition: reality equals information accessible through perception plus measurement instruments. By this operational definition, reality expands with technology. X-ray crystallography revealed atomic structure. Electron microscopes showed virus morphology. Radio telescopes detected pulsars and quasars. Neutrino detectors found solar neutrinos and supernova neutrinos. Gravitational wave interferometers measured space-time ripples. Each instrument extends perception, adding phenomena to verified reality. But this definition makes reality human-centric and technology-dependent. Did X-rays not exist before Röntgen discovered them in 1895? Did neutron stars not radiate before Jocelyn Bell detected their pulses in 1967? A more objective definition might be: reality comprises all phenomena governed by physical law, whether detectable or not. But this definition becomes metaphysical. How can we know what exists beyond all possible detection? The boundary between physics and metaphysics blurs at the edge of observability. The concept of Umwelt, introduced by Jakob von Uexküll in 1909, proposes that each organism inhabits its own perceptual world constructed from sensory inputs and behavioral affordances. A tick's Umwelt contains three key stimuli: butyric acid scent from mammalian skin glands, warmth indicating proximity to blood, and hairless skin for penetration. The tick's reality is impoverished compared to humans, lacking color, sound, form, yet perfectly sufficient for tick survival. Similarly, a bat's Umwelt constructed from echolocation creates three-dimensional acoustic images of the world, experiencing space through temporal delays between emitted chirps and returning echoes. Thomas Nagel's famous 1974 essay, "What Is It Like to Be a Bat?" argued we cannot fully comprehend bat experience because consciousness is fundamentally subjective. Knowing all physical facts about echolocation doesn't reveal what echolocation feels like. Each Umwelt is complete unto itself, the organism's total reality, yet represents only narrow slice of physical world. Instruments extend perception far beyond biological senses, yet themselves have limited bandwidth. Radio telescopes detect frequencies 10 kHz to 300 GHz, but miss higher and lower frequencies. Particle accelerators probe energies to 14 trillion electron volts. The Large Hadron Collider's limit, insufficient to directly produce grand unified theory energy scales at 10 to the 16th GeV, or Planck energy at 10 to the 19th GeV. Gravitational wave detectors sense space-time strains down to 10 to the minus 21st LIGO sensitivity, missing weaker signals from primordial gravitational waves or Planck-scale quantum fluctuations. Neutrino detectors require kiloton-scale masses to catch elusive neutrinos, yet most neutrinos pass through undetected. Each instrument extends reality's boundaries, but encounters fundamental limits from quantum uncertainty, technological constraints, or physics itself. The question arises, what phenomena exist beyond all measurement, even in principle? Are there physical effects forever undetectable, not merely unobserved, but fundamentally unobservable? The observer-dependent versus objective reality debate has ancient philosophical roots. Idealism, championed by George Berkeley, proposes that reality consists of minds and ideas. Material objects exist only when perceived. Esse est percipi. To be is to be perceived. Realism counters that physical world exists independently of observation trees, make sounds falling in forests, regardless of listening ears. Quantum mechanics muddied these waters by revealing observation affects outcomes. Particles exist in superposition of states until measurement collapses possibilities to actuality. Observer and observed are entangled. Does this mean reality is subjective, created by observation? Or does it reveal limitations in classical concepts of objective reality, that asking whether particles have definite properties before measurement is meaningless, like asking what happened before time began? The edge of reality may be where observer-independent description breaks down, where physics cannot separate observer from observed, where subject and object merge. The measurement problem in quantum mechanics. Quantum superposition describes a particle's ability to exist simultaneously in multiple states, multiple positions, velocities, spins, or energies, until measurement forces it to adopt a single definite value. The mathematics of quantum mechanics encodes this through the wave function, denoted by the Greek letter psi, a complex valued function containing all information about a quantum system. The wave function assigns probability amplitudes to each possible measurement outcome, with probabilities calculated by squaring the amplitude's magnitude. An electron's position wave function, for example, might be spread across an entire atom, describing the electron as simultaneously occupying all possible positions with varying probabilities. This isn't merely ignorance about where the electron really is. Experiments confirm the electron genuinely exists in superposition, behaving as a spread-out wave interfering with itself. The electron has no definite position until measurement collapses the wave function, reducing all possibilities to a single observed outcome. Before measurement, asking, "Where is the electron?" is physically meaningless. The electron is everywhere and nowhere. The wave function's mathematical formulation follows Schrödinger's equation, a differential equation describing how psi evolves over time. In isolation, the wave function evolves smoothly and deterministically given initial conditions. Schrödinger's equation predicts future states with complete certainty. The system explores all possible states in superposition, with interference between different components creating the characteristic wave behavior, producing quantum phenomena like tunneling through barriers and quantized energy levels. However, measurement introduces discontinuous, non-deterministic collapse. When an observable-like position is measured, the wave function instantaneously collapses from spread-out superposition to a localized spike at the measured value. The collapse is random, repeating identical measurements on identically prepared systems yields different outcomes distributed according to probability amplitudes squared. After collapse, the system occupies the measured state, and subsequent evolution proceeds via Schrödinger's equation until the next measurement. This dual evolution, smooth deterministic between measurements, discontinuous random during measurements, constitutes the measurement problem. Schrödinger's cat, the famous thought experiment proposed in 1935, illustrates superposition's apparent absurdity when extended to macroscopic objects. A cat is sealed in a box with a quantum device, a radioactive atom that has 50% probability of decaying within 1 hour, triggering a mechanism that shatters a vial of poison, killing the cat. According to quantum mechanics, the atom exists in superposition of decayed and not decayed states until measured. Therefore, Before opening the box to observe the outcome, the cat exists in superposition of alive and dead states. The cat is neither definitively alive nor dead, but both simultaneously, a quantum zombie hovering between existence and non-existent. Only upon observation does the wave function collapse, forcing the cat into one state or the other. Schrödinger intended this as reductio ad absurdum, demonstrating that applying quantum superposition to everyday objects produces ridiculous conclusions. Yet experiments confirm superposition exists for increasingly large systems, molecules containing hundreds of atoms, diamonds with trillions of atoms vibrating in superposition, even superconducting loops with billion to billion electrons flowing simultaneously, clockwise and counterclockwise. The Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg in the 1920 seconds, handles the measurement problem by asserting that observation fundamentally creates reality. Before measurement, quantum systems exist only as potentialities described by wave functions. Measurement actualizes one potential reality, with probabilities given by quantum mechanics. The wave function doesn't describe objective reality, but knowledge about possible measurement outcomes. Questions about unmeasured properties are meaningless, asking what the electron's position was before measurement is like, asking what happened before time began. The Copenhagen interpretation divides the world into quantum systems governed by Schrödinger's equation and classical measuring apparatuses that collapse wave functions. The cut between quantum and classical is arbitrary and observer-dependent, leading to philosophical difficulties. Why do macroscopic objects behave classically? Where exactly does the quantum classical boundary lie? What qualifies as measurement? Does it require consciousness, or does any interaction suffice? The many worlds interpretation, proposed by Hugh Everett in 1957, eliminates wave function collapse entirely by asserting that all measurement outcomes occur in different branching universes. When Schrödinger's cat is observed, the universe splits. In one branch the atom decayed and the cat is dead. In another branch the atom didn't decay and the cat lives. Both outcomes are equally real, occurring in parallel realities that decohere and stop interfering with each other. Every quantum measurement spawns new branches exploring all possible outcomes. There is no collapse, only branching, creating countless parallel worlds containing every possible history. In many worlds, the wave function always evolves. According to Schrödinger's equation, the entire multiverse has a wave function that never collapses. Probability emerges from self-location uncertainty. You don't know which branch you'll experience subjectively, though all branches exist objectively. Many worlds multiplies entities beyond necessity, infinite parallel universes, to avoid one problematic postulate. Yet it's mathematically the simplest interpretation, requiring only Schrödinger's equation without additional collapse mechanisms. Pilot wave theory, or de Broglie-Bohm theory, developed by Louis de Broglie in 1927 and extended by David Bohm in 1952, restores determinism by proposing particles always have definite positions guided by the wave function acting as a pilot wave. The particle follows trajectories determined by the wave's gradient, a quantum potential derived from wave function shape. The wave explores all paths simultaneously, but the particle travels one specific trajectory, guided by wave dynamics. Measurement reveals pre-existing particle positions, not collapsing wave functions, but merely revealing hidden variables. Pilot wave theory reproduces all quantum predictions while maintaining deterministic evolution and objective reality, independent of observation. However, it requires non-locality. The pilot wave must instantaneously coordinate particles across space to produce quantum correlations like entanglement. Additionally, most physicists find pilot waves ontologically extravagant. Why does the wave exist if only particle positions matter physically. Despite these issues, pilot wave theory proves quantum mechanics compatible with determinism and realism, showing measurement problems admit multiple conceptual solutions with identical empirical predictions. The measurement problem asks, why and how does observation collapse wave functions? What physical process distinguishes measurement from other interactions? Does consciousness play a role, or is decoherence environmental interactions destroying quantum coherence sufficient to explain apparent collapse? These questions remain unresolved after a century of quantum mechanics. Decoherence explains why macroscopic objects appear classical environmental interactions rapidly entangle quantum systems with surroundings, spreading coherence across huge numbers of particles, and suppressing observable interference. But decoherence doesn't solve the measurement problem. It explains why we don't see superpositions of macroscopic objects, not why individual measurement outcomes are selected from superposed possibilities. The fundamental question persists. Does reality exist independent of observation? Or does measurement participation create reality? Quantum mechanics works perfectly for predictions, yet reveals profound gaps in understanding reality's nature. The edge of reality appears where observation meets the quantum world, where subject cannot be separated from object, where asking what exists beyond measurement encounters fundamental limit. Quantum uncertainty and the Planck scale. Heisenberg's uncertainty principle, formulated in 1927, establishes fundamental limits on simultaneous knowledge of complementary properties like position and momentum, or energy and time. The principle is expressed mathematically as delta x times delta p greater than or equal to h bar divided by 2, where delta x represents position uncertainty, delta p momentum uncertainty, and h bar equals Planck's constant divided by 2 pi, approximately 1.05 times 10 to the minus 34th joule seconds. This means reducing position uncertainty increases momentum. Uncertainty proportionally measuring a particle's position precisely makes its momentum completely uncertain, and vice versa. Similarly, delta E times delta T greater than or equal to h bar divided by 2 limits simultaneous knowledge of energy and time. These are not measurement limitations, reflecting instrument inadequacy, but fundamental properties of nature. A particle doesn't have definite simultaneous position and momentum. These complementary properties are fundamentally incompatible. Attempting to measure both with arbitrary precision is meaningless, like asking what color prime numbers have. Uncertainty isn't ignorance, but intrinsic indeterminacy woven into reality's fabric. The uncertainty principle isn't a limitation of measurement technology, but fundamental nature of quantum systems. Classical physics assumes particles have definite positions and momenta regardless of measurement, with uncertainty reflecting observer ignorance. Quantum mechanics reveals this assumption. False particles genuinely lack definite complementary properties simultaneously. The act of measurement doesn't disturb pre-existing properties, but actualizes one property at the expense of the complementary property. Measuring position precisely by confining a particle to small region increases momentum spread through quantum confinement effects. The particle bounces unpredictably within the confinement, momentum becoming uncertain. This isn't measurement disturbing momentum, but quantum mechanics forbidding simultaneous definite values. The uncertainty principle manifests physically in zero-point energy even at absolute zero temperature. Quantum systems retain residual energy because position momentum uncertainty prevents particles from sitting motionless at definite positions, violating uncertainty limits. Uncertainty is woven into nature at its most fundamental level. Planck length, approximately 1.616 times 10 to the minus 35th meters, represents the smallest meaningful distance scale in physics calculated from fundamental constants. The square root of g times h bar divided by cubed, where g is Newton's gravitational constant, h bar is reduced Planck's constant, and c is light speed. At scales approaching Planck length, quantum mechanics and general relativity both become important. Quantum uncertainty makes gravitational fields fluctuate wildly, and space-time geometry becomes subject to quantum indeterminacy. Below Planck length, the notion of distance becomes physically meaningless. Attempting to probe smaller scales requires concentrating enormous energy into tiny volumes, creating micro black holes whose event horizons obscure what they were meant to reveal. The Planck length might represent fundamental pixelation of space-time discrete minimal units, rather than continuous manifold, though no experimental evidence confirms or refutes this speculation. Regardless, Planck length marks where classical concepts of geometry and measurement break down completely. Planck time, approximately 5.391 times 10 to the minus 44th seconds, equals the time light takes to traverse one Planck length, representing the shortest meaningful duration. Calculated as the square root of g times h bar divided by c to the fifth, Planck time defines the temporal resolution at which spacetime structure becomes quantum foam. Events separated by less than Planck time cannot be temporally ordered in observer-independent way. Quantum fluctuations of metric make causal ordering ambiguous. Time before Planck, time after the Big Bang is undefined, or at minimum, requires quantum gravity theory to describe. The universe's age, at Planck time 5.39, 1 times 10 to the minus 44th seconds, after the Big Bang, represents the earliest moment about which physics can meaningfully speak, given current understanding. Earlier times might exist in some quantum gravity theory, or the question might be meaningless, like asking what's north of the North Pole. Planck time marks where classical time concept dissolves into quantum indeterminacy. Planck energy, approximately 1.22 times 10 to the 19th GeV, or 1.956 times 10 to the 9 joules, equivalent to automobile at highway speed, represents the energy scale where gravity becomes quantum, mechanically strong. At Planck energy, an elementary particle's Compton wavelength equals its Schwarzschild radius, meaning quantum mechanical size equals gravitational size. Particle interactions at Planck energy produce micro black holes, making standard quantum field theory inapplicable. The Large Hadron Collider achieves maximum 14 tera-electronvolts, roughly 10 to the minus 6th Planck energy, far below regimes where quantum gravity dominates. Achieving Planck energy in laboratory would require particle accelerator with circumference comparable to Milky Way galaxy, powered by entire civilization's energy output. Planck energy physics remains purely theoretical, accessible only through cosmological observations of the very early universe, or through indirect signatures like proton decay. If grand unified theories predict decay at rates detectable by current experiments, Planck energy marks where all fundamental forces unify and quantum gravity determines physics. Space-time becomes quantum foam below the Planck scale, where Heisenberg uncertainty applied to gravitational fields causes space-time geometry to fluctuate violently. Just as electromagnetic fields fluctuate quantum mechanically, creating virtual particle-antiparticle pairs that briefly pop into existence then annihilate, gravitational fields fluctuate, creating microscopic wormholes, baby universes, and topological complexity at Planck scales. The smooth, continuous space-time of general relativity emerges from averaging over these wild fluctuations, much as a smooth water surface emerges from averaging molecular chaos. At Planck scale, notions of distance, duration, causality, and even topology become uncertain. Space-time might not be fundamental, but emergent from deeper quantum structure. Loop quantum gravity proposes space-time is quantized into discrete units called spin networks, with edges carrying quantized areas and volumes. String theory suggests space-time has additional compactified dimensions and emerges from vibrating strings' collective behavior. Regardless of quantum gravity's correct formulation, Planck's scale represents where classical space-time breaks down. Classical space-time, a smooth, continuous four-dimensional manifold, becomes inadequate below Planck's scale, where geometry itself is subject to quantum uncertainty. The metric defining distances and angles fluctuates quantum mechanically, making light cone structure ambiguous and causality uncertain. Attempts to measure space-time curvature precisely require concentrating energy into small volumes, but excessive energy curves space-time so severely that black holes form, hiding the very structure being probed. This fundamental limitation suggests space-time isn't fundamental, but approximate emergent description valid only at scales far above Planck length. Quantum gravity theories attempt to describe the microscopic structure from which space-time emerges, whether discrete spin networks, vibrating strings, or something more exotic, but lack experimental guidance. The Planck scale represents the edge where physics transitions from measurable science to speculative quantum gravity, where familiar concepts like distance and time dissolve into quantum indeterminacy, where reality itself becomes fundamentally uncertain. Reality as fundamentally probabilistic rather than deterministic follows inevitably from quantum mechanics. Unlike classical physics, where knowing all initial conditions determines all future states with certainty, quantum mechanics provides only probability distributions over outcomes. The wave function evolves deterministically via Schrödinger's equation, but measurement produces inherently random results distributed according to probabilities calculated from wave function's squared magnitude. This randomness is irreducible, not due to hidden variables or incomplete knowledge, but fundamental to nature. Einstein famously objected, insisting, "God does not play dice," but experiments testing Bell's inequalities have confirmed quantum mechanics over local hidden variable theories, proving nature is genuinely indeterministic or non-local, or both. The universe at its foundations is probabilistic, not mechanical clockwork. Reality doesn't follow predetermined script, but unfolds through cascading random quantum events. Free will might reside in this quantum indeterminacy, consciousness might harness quantum randomness, or determinism might emerge statistically from quantum chaos. The edge of reality, where quantum meets classical, is where determinism gives way to fundamental uncertainty, extra dimensions beyond 3 space. String theory, the leading candidate for unifying quantum mechanics and general relativity, requires space-time to have 10 or 11 dimensions rather than the familiar 4 of everyday experience, 3 spatial plus 1 temporal. The extra 6 or 7 spatial dimensions must exist, but are compactified, curled up at extremely small scales, typically the Planck length of 10 to the minus 35th meters. These compactified dimensions form complex geometric shapes called Calabi-Yau manifolds, 6-dimensional spaces satisfying specific mathematical properties required for string theory's consistency. Different Calabi-Yau shapes produce different low-energy physics. The vast landscape of 10 to the 500th possible compactifications corresponds to different possible universes with varying particle masses, force strengths, and physical constants. The compactification scale determines why extra dimensions are invisible. At macroscopic scales, they're too small to detect, but at Planck energies, all dimensions become equally significant and accessible. Kaluza-Klein theory, proposed by Theodore Kaluza in 1921 and extended by Oscar Klein in 1926, first demonstrated that extra dimensions might unify fundamental forces. Kaluza showed that Einstein's general relativity in 5 dimensions 4 space plus 1 time, naturally contains both gravity and electromagnetism. The 5th dimension's components of the metric tensor describe electromagnetic fields, while 4-dimensional components describe gravity. Klein proposed the 5th dimension is compactified into a tiny circle, too small to observe directly but affecting particle physics through quantized momentum in the extra dimension, manifesting as electric charge. Kaluza-Klein theory predicts massive particles, called Kaluza-Klein modes, excited states with momentum in the extra dimension that haven't been observed, constraining extra dimension size to below Large Hadron Collider's energy reach. Modern Kaluza-Klein theories extend to multiple dimensions and non-abelian gauge symmetries, attempting to unify all forces geometrically. Brain-world scenarios emerging from string theory and M theory in the late 1992 propose our entire observable universe is a 3-dimensional membrane, a 3-brane embedded in higher dimensional space, called the bulk. Standard model particles and forces are confined to the brain like dust on a surface, while gravity propagates through the bulk, interacting with all dimensions. This explains gravity's weakness. Gravitational force spreads through extra dimensions and thus appears diluted on our brain compared to other forces confined to 3 dimensions. Multiple brains might exist in the bulk, representing parallel universes occupying the same higher dimensional space but separated along extra dimensions, forever invisible to each other except through gravity. Collisions between brains might produce big bangs, with our universe's origin being one such collision. Brainworld cosmology radically reimagines space's nature and universe's origin. The bulk in brainworld models is the higher dimensional space containing brains, analogous to 3-dimensional space containing 2-dimensional surfaces. In simplest scenarios, the bulk has one extra large dimension in addition to the 3 on our brain, making 5-dimensional space-time total. More complex models involve multiple extra dimensions, some large and some compactified. Gravity's ability to access the bulk explains why it's weaker than other forces. Electromagnetic, weak, and strong forces are confined to our 3-brane, concentrating their strength, while gravity spreads through bulk volume, diluting along extra dimensions. Objects in the bulk, if they exist, would be completely invisible to us, except through gravitational influence, detectable only by missing energy in particle collisions or anomalous gravitational effects. The bulk might contain dark matter, parallel universes, or exotic structures inaccessible to direct observation. Large extra dimensions, proposed in the ADD model by Arkany Hamed, Dimopoulos, and Valley in 1998, suggest some extra dimensions might be much larger than Planck's scale, potentially as large as millimeters. This radical idea addresses the hierarchy problem why gravity is 10 to the 32nd times weaker than other forces by proposing the Planck scale appears large in our 3D perspective, but is actually much smaller in higher dimensional perspective. If gravity spreads through millimeter scale extra dimensions, while other forces are confined to our brain, observed weakness is geometric dilution rather than fundamental strength difference. Large extra dimensions predict deviations from Newton's inverse square law at sub-millimeter distances, testable through precise short-range gravity measurements. They also predict black hole production at LHC energies if fundamental Planck scale is low, though no such black holes have been observed, constraining extra dimension size. Warped extra dimensions, proposed by Lisa Randall and Raman Sundram in 1999, use non-Euclidean geometry to hide extra dimensions without requiring small compactification. In RS models, an extra dimension connects 2 brains, our visible brain and a hidden gravity brain. The extra dimension has warped geometry with exponentially varying metric, meaning distances measured in the bulk differ dramatically from distances on branes. Gravity is localized on the gravity brane, appearing weak on our brain due to exponential warping suppressing gravitational influence. Unlike large extra dimensions requiring multiple extra dimensions, warped models work with single extra dimension of potentially infinite extent. Warping explains hierarchy problem geometrically and predicts Kaluza-Klein graviton resonances potentially detectable at LHC. Warped dimensions represent space-time curvature in extra dimensions, demonstrating that extra dimensions need not be compactified or large to be consistent with observation's exotic geometry suffices. Whether consciousness or information might exist in extra dimensions remains speculative but intriguing. If reality has additional dimensions beyond the three spatial dimensions accessible to matter and forces, perhaps consciousness, which seems not to be purely spatial, extends into these dimensions. Subjective experiences' apparent non-locality and unity might reflect connections through higher dimensional space inaccessible to physical measurement. This is pure speculation without scientific evidence, but extra dimensions offer conceptual space for dualism, mental and physical, occupying different dimensional subspaces of reality. Alternatively, if information is fundamental rather than matter, perhaps information exists in higher dimensional configuration space, with our three-dimensional reality being a projection or shadow. The holographic principle, discussed in the next chapter, formalizes this idea mathematically. Extra dimensions reshape our conception of space itself, suggesting reality might have more structure than accessible through normal perception and measurement, with aspects of existence perhaps including consciousness residing beyond the three-dimensional edge. The holographic principle. Black hole entropy, discovered by Jacob Bekenstein in 1973 and refined by Stephen Hawking in 1974, is proportional to the event horizon's surface area rather than the black hole's volume. This seems paradoxical. Thermodynamic systems typically have entropy proportional to volume, reflecting the number of microscopic states, which should scale with number of particles and thus volume. But black holes violate this expectation. Entropy equals 1/4 the horizon area in Planck units. S equals A divided by 4 times G times H bar divided by cubed. A black hole containing all matter in a galaxy has entropy proportional to its two-dimensional horizon area, not its three-dimensional interior volume. This suggests information about the three-dimensional interior is encoded on the two-dimensional surface, as if the volume's physics is holographic projection from boundary data. Bekenstein-Hawking entropy implies black holes contain maximum possible entropy for a given volume, saturating a fundamental bound relating information to spatial region size. The holographic principle, formulated by Gerard 't Hooft in 1993 and refined by Leonard Susskind in 1995, generalizes black hole entropy to propose that any three-dimensional region's information content is bounded by its two-dimensional boundary area measured in Planck units. The maximum entropy and thus information contained in volume V is proportional to surface area A, not volume, with maximum entropy Smax equals A divided by 4 times Planck area. This implies that three-dimensional space might be holographic. All information in a volume can be encoded on its boundary, with interior physics derived from boundary data like a hologram, reconstructing three-dimensional images from two-dimensional interference patterns. If holographic principle is fundamental, our three-dimensional reality might be projection of information encoded on a distant two-dimensional surface, perhaps at cosmological horizon or in some deeper formulation. The holographic principle suggests spatial dimensionality might be illusory, with reality fundamentally lower dimensional than appearance suggests. Add S, CFT correspondence, discovered by Juan Maldacena in 1997, provides concrete mathematical realization of holographic principle by demonstrating exact equivalence between quantum gravity in anti-de Sitter space and negatively curved spacetime and conformal field theory on its boundary. Gravity in 5-dimensional ADS bulk equals quantum field theory without gravity on 4-dimensional boundary. Every gravitational process in the bulk corresponds to quantum field process on the boundary, and vice versa. Strong coupling in boundary theory corresponds to weak coupling in bulk gravity, allowing calculations intractable in one description to be performed in dual description. ADS CFT is holographic. Higher dimensional gravitational theory is completely encoded in lower dimensional quantum theory without gravity. Although our universe isn't anti-de Sitter space, ADS, CFT provides proof of principle that holographic theories exist and suggests similar correspondence might apply to our universe, with physics in our 3-dimensional space encoding quantum information on a 2-dimensional cosmological horizon or other boundary. If our 3-dimensional reality is holographic projection of 2-dimensional information, profound implications follow for understanding space, matter, and consciousness. Particles, fields, and space-time itself would be emergent structures derived from more fundamental 2-dimensional quantum information. The hologram wouldn't be illusion. Our 3-dimensional experience is real, but its fundamental description requires only boundary data. Asking what happens inside volumes becomes secondary to understanding boundary encoding. This resembles how a photograph contains all visual information about a 3-dimensional scene, despite being 2-dimensional depth, is inferred from perspective cues and shading. Similarly, our perception of 3-dimensional space might be reconstruction from 2-dimensional fundamental reality. Whether consciousness is holographic, perhaps encoded on 2-dimensional neuronal networks, reconstructing 3-dimensional mental space remains speculative. The holographic principle transforms our conception of space from fundamental arena to emergent hologram. Planck scale pixels represent the fundamental information units if space is holographic. Each Planck area, 1.6 times 10 to the minus 70th square meters, encodes 1 bit of information according to holographic principle's maximum entropy bound. The observable universe's cosmological horizon has area approximately 10 to the 123rd Planck areas, corresponding to maximum entropy 10 to the 123rd bits. If this entropy saturates the bound, our 3-dimensional observable universe's information content equals the 2-dimensional horizon's information, with roughly 10 to the 123rd bits total, the universe's ultimate information capacity. Below Planck's scale, the notion of continuous space might break down into discrete pixels, though whether space is fundamentally discrete or continuous remains unknown. Holographic pixel size represents information density's ultimate limit, constraining how much information can be stored in spatial regions. Experimental searches for holographic noise attempted to detect Planck-scale graininess of spacetime by searching for random fluctuations in positions and times at scales approaching Planck length. The GO600 gravitational wave detector in Germany observed mysterious noise in 2008 that some speculated might be holographic jitter, quantum fluctuations of spacetime itself, creating measurable noise in interferometer arm lengths. However, subsequent analysis attributed the noise to instrumental artifacts rather than quantum spacetime. Fermilab's holometer experiment, completed in 2015, specifically searched for holographic noise by comparing 2 co-located interferometers and searching for correlated position fluctuations that would indicate holographic degrees of freedom. The holometer found no evidence for holographic noise down to sensitivities approaching Planck scale, constraining some holographic models. However, Absence of evidence isn't evidence of absence. Many holographic models don't predict detectable noise, and space-time might be holographic without producing observable fluctuations at experimentally accessible scales. Reality as information rather than physical substance represents philosophical shift from material realism to information theoretic ontology. If holographic principle is correct, then information not matter or energy is fundamental, with physical reality being information's manifestation. This resembles digital physics and Wheeler's it from bit proposal that every physical quantity derives from binary choices, bits of information obtained through quantum measurements. In information-centric view, particles are information processing patterns, forces are information transfer protocols, and space-time is information's geometric organization. Consciousness might be information integrated in specific patterns. Life is information that self-replicates and evolves, and universe is vast information processing system obeying quantum information's laws. Whether information is more fundamental than physical substrate, or whether information requires physical substrate to instantiate remains debated. The holographic principle suggests we might be living in information holographically projected as three-dimensional reality, a cosmic hologram where the edge of reality is literally a two-dimensional screen. Simulation hypothesis. Nick Bostrom's simulation argument, published in 2003, presents a trilemma claiming at least one of three propositions must be true. Civilizations go extinct before reaching technological maturity capable of running ancestor simulations. Technologically mature civilizations choose not to run ancestor simulations despite capability, or we are almost certainly living in a computer simulation. The logic proceeds. If civilizations survive to technological maturity and run ancestor simulations, detailed simulations of their evolutionary history, then simulated beings vastly outnumber original beings, because each advanced civilization runs many simulations containing billions of simulated conscious beings. If simulated beings outnumber real beings by factors of thousands or millions to one, then randomly selected conscious observer is probably simulated rather than original. Therefore, either civilizations don't survive, don't simulate, or we're simulated. Bostrom doesn't claim we're definitely simulated, but argues simulation hypothesis deserves serious consideration given its logical structure. The argument rests on computational substrate independence. Consciousness doesn't require biological neurons, but emerges from any substrate implementing appropriate information processing. Computational universe hypothesis, championed by physicists including Konrad Zuse, Ed Fredkin, and Stephen Wolfram, proposes that physical reality is computational process. The universe is literally a computer executing program that generates all phenomena. In this view, fundamental physics consists of discrete update rules applied to cellular, automaton, or quantum computation, with spacetime, particles, and forces emerging from computational substrates' behavior. Wolfram's A New Kind of Science argues that simple cellular automaton rules can generate complex structures resembling particle physics and cosmology, suggesting universe might run on similarly simple algorithms at Planck scale. Digital physics proposes universe is discrete rather than continuous, operating on quantized space, time, and information. If universe is computational, then questions arise. What is hardware? What is source code? Who or what designed the program? Or is universe self-executing, with no external creator needed, just mathematical structure instantiating itself? If the observable universe contains approximately 10 to the 80th atoms, this corresponds to roughly 10 to the 90th bits of information needed to specify all particle positions and states at classical level. Quantum mechanically, specifying the entire observable universe's quantum state requires exponentially more information. Each particle can be in superposition of states, and n particles have quantum state space with dimensions 2 to the nth, quickly becoming astronomically large. However, the holographic principle bounds maximum information at 10 to the 123rd bits based on cosmological horizon area. Advanced civilizations with computational resources approaching this limit could simulate universes, though simulating quantum states exactly requires simulating quantum computers. Classical simulations might suffice if only conscious observers' experiences need rendering the vast majority of universe might remain uncomputed until observed, like video game environments loading only when players approach. Simulation efficiency might rely on information compression and approximations undetectable to simulated beings. Quantum computers might enable universe simulations by naturally handling quantum superposition and entanglement that classical computers struggle to simulate efficiently. A quantum computer with 300 qubits can exist in superposition of 2 to the 300th states, more than atoms in the observable universe, allowing compact representation of quantum systems that would overwhelm classical computation. If universe is fundamentally quantum, simulating it faithfully requires quantum computation. Advanced civilizations might build quantum computers approaching universe's information content, 10 to the 123rd qubits or quantum bits, sufficient to simulate universes indistinguishable from base reality. Whether such computers can be built faces physical limits from thermodynamics and quantum error correction requirements, but no fundamental obstacle prevents quantum computers from simulating universes given sufficient resources. This makes simulation hypothesis technologically plausible for sufficiently advanced civilizations, lending credence to Bostrom's argument. Glitches in reality, apparent anomalies like the Mandela effect where large groups misremember historical details identically, déjà vu where experiences feel eerily familiar, or quantum tunneling where particles traverse barriers they classically shouldn't have been half seriously proposed as simulation bugs or rendering errors. The Mandela effect, where many people remember Nelson Mandela dying in prison in the 1,980 seconds despite his actual death in 2013, might reflect simulation branching or memory database errors. Déjà vu might occur when simulation reloads previous state or when pattern matching algorithms misfire. Quantum phenomena like superposition, entanglement, and tunneling might be computational optimizations simulating only measured observables rather than definite properties, using non-local correlations for efficient information encoding, allowing particles to jump discontinuously when exact trajectories aren't rendered. These speculations are unfalsifiable and arguably pseudoscientific, but they illustrate how simulation hypothesis invites reinterpreting mysterious phenomena as computational artifacts rather than fundamental physics. Fine-tuned physical constants, the cosmological constant, electron mass, strong force coupling, and dozens of other parameters that seem precisely adjusted for chemistry, stars, and life suggest programmed universe. If constants differed by small percentages, atoms would be unstable, stars wouldn't form, or chemistry wouldn't produce complexity. This apparent fine-tuning invites explanation. Random chance across infinite multiverse, making some universes life-compatible. Anthropic selection, where observers necessarily find themselves in rare life-supporting universes. Or intelligent design including simulation hypothesis, where programmers tuned parameters for specific outcomes. Simulation hypothesis neatly explains fine-tuning programmers set initial conditions and constants to produce interesting emergent complexity like life and consciousness, just as game designers tune parameters for engaging gameplay. Natural selection of universes, or anthropic principles, provide alternative explanations without invoking simulators, but fine-tuning lends plausibility to the idea that reality's fundamental constants might be programmed rather than determined by deeper theory. The Fermi paradox, the puzzling absence of detectable alien civilizations, despite billions of potentially habitable planets, gains novel resolution if simulation hypothesis is correct. Simulated universes might be more common than base reality, meaning most apparent universes are simulations. If our universe is simulation, other civilizations might be non-player characters with scripted behaviors rather than independent conscious beings. Or they might exist, but be separated through simulation compartmentalization, preventing contact. Alternatively, civilizations might discover they're simulated and achieve transcendence by escaping simulation or communicating with simulators, explaining their disappearance, or perhaps creating simulations. Is universal attractor all advanced civilizations transition to running simulations rather than space exploration, choosing virtual worlds over physical reality. The Fermi paradox's resolution might be that we're not observing base reality's universe, but simulations' limited rendering designed to isolate conscious observers for experimental or entertainment purposes. Observable universe's apparent loneliness becomes test chamber rather than cosmic oversight. Can we prove we're in a simulation? The answer appears to be no. Simulation hypothesis is fundamentally unfalsifiable, like skeptical scenarios of Descartes' evil demon or brain in vat. Any evidence for simulation could be programmed simulation feature. Any physical law could be source code. Any anomaly could be either bug or intended feature. Nested simulations compound the problem. If simulations can run simulations recursively, base reality becomes epistemically inaccessible, lost in infinite regression. Even if we detected obvious simulation artifacts, we couldn't know whether we found evidence of our simulation or evidence programmed into simulation to mislead us. Some argue that very unfalsifiability makes simulation hypothesis unscientific metaphysics rather than physics, while others counter that Bayesian reasoning can assign probabilities to unfalsifiable hypotheses based on simplicity and explanatory power. Simulation hypothesis forces confrontation with epistemological limits. The edge of reality might be computational substrate, forever beyond empirical access, knowable only through philosophical reasoning about what kinds of realities could exist and which we likely inhabit. The particle horizon and observable limits. The observable universe extends 93 billion light-years in diameter, 46.5 billion light-years in every direction, encompassing all regions from which light could have reached us during the 13.8 billion years since the Big Bang. This particle horizon defines the boundary of our causally connected region, the edge beyond which no signal has yet arrived, and none will arrive before dark energy acceleration carries those regions permanently beyond reach. The horizon's size exceeds light travel distance because cosmic expansion stretched space during photon transit, carrying emission points farther away continuously while light traveled towards us. In today's coordinates accounting for expansion, the most distant observable light originated from regions now located 46.5 billion light-years away, despite traveling only 13.8 billion years. This represents our cosmic edge, not a physical boundary, but an observational horizon, beyond which lies more universe, possibly infinite, forever hidden from view. The particle horizon bounds knowable reality operationally. Everything beyond is metaphysics rather than physics, accessible only through theoretical extrapolation and assumptions. The particle horizon encompasses the maximum extent of causally connected space, all regions with which we could have exchanged information, given the universe's finite age and light's finite speed. Causality operates at light speed maximum, so the horizon marks how far causal influences could have propagated since the Big Bang. Regions beyond the particle horizon are causally disconnected. No signal from there has reached here. No signal from here has reached there. And no physical process has yet connected these regions. This disconnection is not merely current, but historical. These regions have never been in causal contact since inflation ended and normal expansion began. If the universe is infinite, infinitely many such disconnected regions exist, each with their own observable universes centered on hypothetical observers there. The particle horizon divides reality into the observable, everything within 46.5 billion light-years, subject to empirical study, and the unobservable, everything beyond, accessible only through cosmological principles' assumption that unobserved regions resemble observed regions statistically. The cosmic microwave background surface represents the most distant structure observable electromagnetically, located at co-moving distance 46.1 billion light-years, just inside the particle horizon. This surface marks recombination epoch 380,000 years after the Big Bang, when neutral hydrogen formed and photons decoupled from matter, streaming freely as cosmic microwave background radiation. We observe the CMB as microwave photons arriving from all directions, the oldest light in the universe, carrying information about conditions when the universe was 0.003% its current age. The CMB surface is our electromagnetic horizon. Earlier epochs were opaque because photons scattered constantly off free electrons in ionized plasma, preventing propagation. No electromagnetic observation can penetrate earlier than 380,000 years post-Big Bang. However, gravitational waves and neutrinos decouple earlier neutrinos at 1 second. Gravitational waves, potentially from inflation itself, offering windows to pre-recombination epochs if detectors achieve sufficient sensitivity. But for electromagnetic astronomy, the CMB marks the ultimate edge, the oldest and most distant light accessible. The event horizon, located approximately 16 billion light-years away in co-moving coordinates, defines the future visibility limit, the boundary beyond which regions recede so fast due to dark energy acceleration that light emitted now will never reach us regardless of waiting time. Dark energy causes cosmic expansion to accelerate, making distant regions recede at velocities exceeding light speed once beyond the event horizon. Photons emitted toward us from beyond the horizon are swept away by expansion faster than they can approach, unable to close the distance. Over trillions of years, the event horizon will contract as acceleration increases, eventually bringing galaxies currently visible but distant across the boundary, causing them to fade from view permanently and disappear beyond the edge. In 150 billion years, only the local group and nearby groups within approximately 10 million light-years will remain visible. Everything beyond will have crossed the event horizon into permanent observational darkness. The event horizon represents the edge of forever. What crosses it is lost to observation eternally, information permanently inaccessible, reality beyond retrieval. The question of whether infinite space exists beyond the particle horizon depends on the universe's global geometry. Observations indicate flat spatial geometry. Within measurement precision, parallel lines remain parallel, triangles have 180-degree angle sums, spatial curvature is 0 within 0.5%. Flat infinite universes extend infinitely in all directions, never curving back on themselves. If our universe is flat and unbounded, as observations suggest, then infinite space exists beyond the horizon, containing infinitely many galaxies, stars, and planets we can never observe. Alternatively, the universe might be finite but unbounded, spatially closed like a hypersphere's three-dimensional analog, where traveling far enough in any direction returns you to the starting point without encountering boundaries. Current observations constrain minimum size of closed universes to exceed the observable universe by at least factor 250 based on searches for topological signatures in the CMB. Whether space is infinite or merely vastly larger than observable remains unknown and might be fundamentally unknowable. We can only observe our finite patch. Causally disconnected regions beyond the particle horizon might have different physics if symmetry breaking during cosmic phase transitions produced different vacuum states in different regions. String theory's landscape predicts 10 to the 500th possible vacuum configurations, each corresponding to different low-energy effective field theories with varying particle masses, force coupling strengths, and cosmological constants. During rapid expansion or inflation, different regions might settle into different vacua as symmetries broke, creating patchwork multiverse with locally different physics. Our observable universe's physics standard model particles and forces, specific coupling constants, particular mass ratios, might be one possibility among countless variants realized in causally disconnected regions. If physical laws vary beyond the horizon, the cosmological principle assuming uniformity on large scales breaks down globally, even if locally valid. We would inhabit one physics patch among infinite variety, with most regions inhospitable to chemistry, structure, or observers. Anthropic selection would explain why we observe life-compatible physics we couldn't exist elsewhere. Superhorizon modes are density fluctuations, with wavelengths exceeding the particle horizon, created during inflation when quantum fluctuations stretch to scales larger than the horizon. These modes affect our observable universe's properties, despite extending far beyond observable limits. Inflation predicts nearly scale-invariant primordial fluctuations across all scales, from subatomic to superhorizon. The largest observable fluctuations visible in the CMB have wavelengths approaching the horizon size. These are partially superhorizon, with most of their wavelength lying beyond observable limits. We observe only small fraction of these modes' oscillation, seeing essentially DC offsets or gradients rather than complete waves. Superhorizon modes could create preferred directions if a mode's gradient points toward a specific direction, or large-scale flows if modes create net density gradients extending beyond the horizon. The CMB's hemispherical asymmetry, axis of evil alignment, and possibly dark flow might reflect superhorizon mode influences, though proving this requires distinguishing superhorizon effects from statistical flukes in cosmic variance. Observational horizons define reality operationally by establishing boundaries between empirically testable physics and unfalsifiable metaphysics. Everything within the particle horizon is potentially observable through direct electromagnetic, gravitational wave, or neutrino astronomy, or indirectly through effects on observable matter. Everything beyond the particle horizon is unobservable in principle. No signal from there has reached us, and dark energy ensures most never will as regions cross the event horizon. This creates sharp division. Empirical science studies the observable, metaphysics speculates about the unobservable. Questions about beyond horizon reality, whether it exists, what properties it has, whether physical laws differ, are metaphysical unless they produce observable consequences within the horizon through mechanisms like superhorizon modes or eternal inflation's vacuum variations affecting observable physics. The operational edge of reality coincides with observational horizons. Reality equals what we can observe plus what produces observable effects, with everything beyond being interesting speculation, lacking empirical foundation. Black hole event horizons and information paradox. The event horizon at radius r equals 2 gm divided by c squared, the Schwarzschild radius, marks the boundary of no return where escape velocity equals light speed. For non-rotating black holes, this is spherical surface at distance twice the gravitational radius from singularity. Anything crossing the horizon from outside falls inevitably towards singularity. No force can prevent collapse. No trajectory escapes. Light itself cannot escape once inside, making the interior forever invisible to external observers. The horizon is one-way membrane. Matter and light cross inward freely but cannot return. From outside perspective, infalling objects appear to freeze at the horizon, redshifting asymptotically to infinite wavelength and taking infinite time to cross due to extreme gravitational time dilation. From infalling perspective, nothing special happens at crossing smooth passage with no local barrier. Only after crossing does inevitable doom become apparent, as space-time curvature pulls everything towards singularity in finite proper time. Time dilation approaches infinity at the event horizon due to extreme space-time curvature. Clocks near the horizon run arbitrarily slowly compared to distant observers. The gravitational time dilation factor is square root of 1 minus 2 gm over rc squared, which approaches 0 as r approaches Schwarzschild radius. A clock at the horizon would appear frozen from outside, taking infinite coordinate time to tick once, though finite proper time elapses for the clock itself. This creates coordinate singularity at the horizon, mathematical singularity in standard coordinates, but not physical singularity where curvature diverges. Changing to Kruskal-Seekers or other coordinates removes coordinate singularity, revealing smooth horizon crossing. The physical singularity lies at r equals 0, where curvature diverges infinitely, space-time tears, and general relativity breaks down. Time dilation makes the horizon an effective, one-way temporal barrier. External observers never see anything cross, while infalling observers cross in finite time, experiencing no horizon barrier but inevitable singularity doom. Spaghettification describes tidal forces stretching objects into long, thin shapes as they fall towards singularity. Tidal forces arise from gravity gradient. Closer parts experience stronger pull than farther parts. Near stellar mass black hole horizons, tidal forces exceed structural strength, ripping human bodies apart, with feet pulled more strongly than head by differential gravity exceeding molecular bonds' tensile strength. For supermassive black holes like Sagittarius A star with horizon radius 12 million kilometers, tidal forces at crossing are mild. Human could survive horizon passage intact, experiencing brief normal existence inside before inevitable approach to singularity, where tidal forces eventually dominate and tear everything to atoms, then subatomic particles, before reaching zero radius. Spaghettification is inevitable consequence of radial gravitational gradient, affecting all matter falling towards singularity, though severity depends on black hole mass and distance from center. The firewall paradox, proposed by Almheri, Marolf, Polchinski, and Sully in 2012, suggests black hole horizons might be walls of intense radiation rather than smooth empty space. The paradox arises from combining Hawking radiation, quantum mechanics' no-cloning theorem, and black hole complementarity. Hawking showed black holes emit thermal radiation through quantum tunneling, eventually evaporating completely. Information falling into black holes seems lost, violating quantum mechanics' unitarity. Black hole complementarity resolves this by proposing information both falls inside from infalling perspective and escapes in radiation from external perspective. But AMPs argue complementarity requires violations of either energy positivity or causality unless a firewall of intense radiation exists at the horizon, incinerating anything attempting to cross. This contradicts equivalence principle's prediction of smooth crossing. The firewall paradox remains unresolved, with proposed solutions including complementarity without firewalls, modified quantum mechanics, ER-EPR conjecture linking entanglement to wormholes, or actual firewalls, despite apparent contradictions. The black hole information paradox asks whether information falling into black holes is permanently lost or eventually recovered. Classical general relativity says, yes, information crosses horizon, falls to singularity, and disappears from universe when black hole evaporates via Hawking radiation, which is purely thermal and carries no information about what fell in. But quantum mechanics forbids information loss. Unitary evolution preserves information in quantum states always. Resolving this apparent contradiction has driven quantum gravity research for decades. Proposed solutions include information encoded in subtle correlations in Hawking radiation requiring modifications to thermality predictions, information stored at horizons rather than falling to singularity, information escaping through baby universe formation or wormholes, or genuinely non-unitary physics where quantum mechanics breaks down for black holes. Recent progress suggests holographic principal and AD-CFT correspondence show information is preserved. Black hole evolution is unitary from boundary perspective, though might appear non-unitary from within spacetime. The paradox reveals tensions between quantum mechanics and general relativity requiring quantum gravity resolution. Hawking radiation emerges from quantum field theory in curved spacetime through virtual particle pair production near the event horizon. Vacuum fluctuations constantly create particle-antiparticle pairs that normally annihilate immediately. Near horizons, negative energy particles can fall inside, while positive energy partners escape, creating outward radiation. The negative energy particles have negative mass from horizon perspective. Reducing black hole mass, the black hole evaporates gradually, radiating energy as thermal photons and other particles. Hawking calculated radiation temperature as h bar cubed divided by 8 pi gmk, where k is Boltzmann constant, inversely proportional to mass. Stellar black holes have temperatures nanokelvins, emitting negligibly, but microscopic black holes radiate intensely, evaporating in explosions. Hawking radiation is thermal perfect blackbody spectrum, carrying no information about black hole contents beyond mass, charge, and angular momentum. This information loss created the paradox. Recent calculations suggest subtle correlations in radiation might encode information, though debates continue whether these are calculable or physical. Black hole complementarity, proposed by Susskind, Thorlacius, and Uglum in 1993, attempts resolving information paradox by asserting information both falls inside from infalling observer perspective and escapes in Hawking radiation from external observer perspective, with no observer seeing both descriptions simultaneously. This seems to violate no cloning theorem forbidding copying quantum states, but complementarity argues the two descriptions apply to causally disconnected observers who can never compare notes, making cloning unobservable. From outside, information gradually leaks out in radiation correlations. From inside, information falls to singularity and is destroyed. Both perspectives are valid in their respective reference frames, though globally, the complete description preserves information unitarily when viewed from appropriate boundary perspective. Complementarity is controversial. Critics argue it's semantics rather than physics, while supporters contend its genuine resolution showing quantum mechanics and relativity are consistent when observer dependence is properly accounted for. ER equals EPR, proposed by Maldacena and Susskind in 2013, conjectures that entangled particles are connected by microscopic Einstein-Rosen wormholes. Quantum entanglement and wormhole geometry are equivalent descriptions. In this view, entangled particles aren't mysteriously connected through spooky action at a distance, but connected through geometric wormhole threads in space-time fabric itself. Information doesn't need faster than light transfer because entangled particles connect through wormhole, providing geometric path. For black holes, ER equals EPR suggests Hawking radiation remains entangled with black hole interior through microscopic wormholes, preserving information geometrically and resolving paradox. The conjecture unifies quantum information and geometry, suggesting space-time emerges from entanglement. Interior black hole reality isn't lost, but geometrically connected to exterior through wormhole network, fundamentally inaccessible from outside, but information preserving from holographic boundary perspective. This represents profound reconception of space-time, information, and reality's structure, multiverse level I-infinite space. If the universe is spatially infinite, as flat geometry suggests, then all possible configurations of matter occur infinitely often at sufficient distance. The mathematics is straightforward yet mind-bending. With approximately 10 to the 118th possible quantum states in a Hubble volume, the spherical region within our cosmic horizon, spanning 93 billion light-years diameter and infinite space, containing infinite such Hubble volumes, every possible arrangement of particles must repeat infinitely many times. This isn't speculation, but logical necessity following from quantum mechanics' finite state space and spatial infinity. Statistical calculations based on quantum field theory and combinatorics suggest that an exact copy of you, identical down to every atom, thought, and memory exists approximately 10 to the 1, 0 to the 29, 3 meters away. A distance so vast, it makes the observable universe seem microscopic by comparison. These copies aren't merely similar, but genuinely identical, experiencing identical lives in regions whose initial conditions happened by chance to match ours exactly. The Level 1 multiverse has identical physics everywhere, same standard model particles, same fundamental forces, same coupling constants, same cosmological constant. The variation occurs solely in initial conditions, the specific arrangement of matter and energy emerging from quantum fluctuations during inflation. In one region, fluctuations produced our solar system with Earth, life, and civilization. In another region, 10 to the 1, 0 to the 2/9 meters away, identical fluctuations produced identical solar system, Earth, life, and you reading this identical text. Between these identical regions lie countless variations, Earths where dinosaurs didn't go extinct, where you made different choices, where continents have different shapes, where physics experiments yielded different random quantum outcomes. With infinite space, not only does everything that can happen, but it happens infinitely many times, in infinitely many variations, plus infinitely many exact repetitions. This follows from quantum mechanics and cosmic inflation's predictions without requiring exotic new physics. Inflation, the exponential expansion in the universe's first fraction of a second, stretched quantum fluctuations to cosmic scales, creating the density variations that seeded galaxies and large-scale structure. These fluctuations are random, distributed according to quantum probabilities, but inflation generated them across infinite space. The cosmic microwave background's temperature fluctuations, measured to 1 part in 100,000, reflect these primordial quantum fluctuations. Extrapolating the observed statistical distribution across infinite space inevitably produces every possible fluctuation pattern infinitely often. Observations indicating flat spatial geometry, parallel lines remaining parallel, universe not curving back on itself, suggest space extends infinitely rather than being finite and closed. If space is truly infinite, Level 1 multiverse is unavoidable consequence. The implications are philosophically profound. Everything that can possibly happen within physics laws does happen somewhere in the infinite expanse. Every decision you could make, you do make in some distant region. Every historically possible outcome occurred somewhere worlds where Rome never fell, where industrial revolution happened in China, where nuclear war destroyed civilization, where humanity colonized galaxies. The concept of possibility collapses into actuality distributed across infinite space. What we call counterfactuals, events that could have occurred but didn't, are actual facts occurring in distant regions. Personal identity becomes questionable when infinite identical copies exist. Are they you, or separate individuals who happen to be indistinguishable? If you die here, but identical copies continue elsewhere, have you truly ended? These questions challenge conventional notions of uniqueness, identity, and mortality. The level I multiverse is empirically unverifiable because the regions lie beyond our cosmic horizon, forever causally disconnected and observationally inaccessible. We cannot send signals to or receive signals from regions beyond 93 billion light-years due to light's finite speed and spacetime's expansion. Dark energy's acceleration ensures most regions will remain permanently beyond our event horizon, even given infinite future time. This makes level I multiverse unfalsifiable. We can never observe our copies or alternate histories. Yet the hypothesis follows logically from well-established physics. Quantum mechanics' finite state spaces, inflation's generation of fluctuations, and observations indicating flat geometry. Scientists accept many unobservable entities, quark interiors, black hole singularities, pre-Big Bang epochs, when theory strongly predicts them. Level I multiverse stands on similarly firm theoretical ground despite observational inaccessibility. The boundary between science and metaphysics blurs here. Traditionally, science concerns itself with empirically testable claims, while metaphysics addresses untestable questions about reality's ultimate nature. Level I multiverse occupies ambiguous territory predicted by empirically confirmed theories, yet forever beyond direct observation. Some argue this makes it legitimate physics, others classify it as speculative metaphysics. The distinction might be semantic. If our best theories inevitably imply unobservable consequences, do we accept those implications as part of reality or remain agnostic about phenomena transcending possible observation? The level I multiverse forces confrontation with science's boundaries, what counts as genuine knowledge versus interesting speculation when predictions extend beyond all possible verification. The psychological and existential impact of taking level 1 multiverse seriously can be unsettling. Your life's significance seems diminished if infinite identical copies live identical lives elsewhere. Your choices lack uniqueness when all alternatives are equally actualized in distant regions. Your death is mitigated if consciousness continues in copies. Yet those copies aren't truly you, but separate individuals. The universe's vastness becomes incomprehensible when observable universe represents infinitesimal fraction of total reality. Yet some find comfort in the idea everything you love and value exists eternally across infinite space. Every good outcome is realized somewhere. No possibility is lost, but all are preserved in the infinite ensemble. The level 1 multiverse illustrates how physics discoveries reshape philosophical and psychological understanding of existence, identity, and meaning when reality extends infinitely beyond direct experience and observation. The edge of reality becomes infinite horizon, receding in all directions, with our observable universe as tiny finite island in boundless ocean of space and possibilities. Multiverse level 2, eternal inflation. Eternal inflation creates bubble universes with different physics through variation in symmetry breaking, as inflation ends in different regions. The mechanism operates through quantum fluctuations of the inflaton field, the scalar field driving exponential expansion during inflation. In most regions, quantum fluctuations push the inflaton higher up its potential energy curve, increasing field value and prolonging inflation. In rare regions, fluctuations push inflaton down, causing it to roll to the bottom of its potential, where inflation ends and normal Big Bang expansion begins. Because inflating regions expand exponentially faster than non-inflating regions, inflation-dominated space always exceeds inflation-ended space in total volume, despite continuous nucleation of bubbles where inflation terminates. This creates eternal inflation, globally never-ending inflation with finite bubbles nucleating continuously where inflation locally ends, each bubble containing what inhabitants perceive as their entire universe. String theory's landscape of approximately 10 to the 500th vacuum states, different possible lowest energy configurations of string theory's fields, means different bubbles settle into different effective field theories as inflation ends and symmetries break. The vacuum state determines low energy physics, including which particles exist, their masses, force coupling strengths, space-time dimensions that remain macroscopic versus compactified, and cosmological constant value. Small differences in how inflaton field rolls down its potential or which direction it rolls in the landscape's high-dimensional configuration space produce vastly different final vacuum states. One bubble might settle into vacuum resembling our universe with standard model particles, 4 large space-time dimensions, and tiny positive cosmological constant. Another bubble might settle into vacuum with different particle spectrum, 5 large dimensions, or enormous cosmological constant, causing immediate recollapse. The landscape's 10 to the 500th possibilities ensure incredible diversity across bubble universes. Bubbles nucleate continuously throughout eternally inflating background. Through quantum tunneling, the inflaton field quantum mechanically transitions from false vacuum supporting inflation to true vacuum where inflation ends, creating expanding bubble of true vacuum surrounded by inflating false vacuum. The bubble wall, the boundary between inflating exterior and non-inflating interior, expands at nearly light speed, driven by vacuum energy difference. Inside the bubble, normal Friedmann expansion follows inflation's end, matter and radiation emerge from inflaton field's decay, and cosmic evolution proceeds towards stars, galaxies, and potentially observers. Outside, inflation continues generating new bubbles. Bubbles are causally disconnected, separated by expanding space growing faster than light, preventing any signal exchange. The inflating space between bubbles expands so rapidly that bubbles never collide in most eternal inflation scenarios, though some models allow rare collisions, potentially leaving observable imprints on cosmic microwave background. Our observable universe represents one bubble among infinite variants, distributed across the eternally inflating multiverse. From our internal perspective, we observe only our bubble's 9.3 billion light-year diameter observable region, seeing uniform laws and constants everywhere we look. We cannot observe the bubble wall infinitely far away beyond our cosmic horizon, nor can we see other bubbles beyond the eternally inflating barrier separating us from them. Yet, eternal inflation theory predicts we're one among infinitely many bubbles, most with physics incompatible with our existence. The vast majority of bubbles have vacuum states producing no atoms, no chemistry, no complexity, sterile universes dominated by vacuum energy or immediately collapsing. Only rare bubbles like ours have vacuum states permitting stable matter, long-lived stars, and chemical complexity enabling life and observers. The anthropic principle provides explanation for fine-tuned constants. In our bubble, we necessarily observe bubble compatible with our existence regardless of how rare such bubbles are. If 10 to the 500th vacuum states exist and only 10 to the 10th permit observers, we cannot be surprised finding ourselves in observer-compatible vacuum despite its rarity. We're selected from the ensemble by requirement that observers exist to make observations. This anthropic selection avoids need for fine-tuning explanation. Constants aren't tuned by design or deeper theory, but randomly distributed across bubbles with selection effect ensuring we observe life-compatible values. Critics argue anthropic reasoning is unscientific because it doesn't predict specific values, merely explains them post hoc through selection. Proponents counter that anthropic reasoning makes testable predictions. For instance, cosmological constant should be near minimum value compatible with galaxy formation, which observations approximately confirm. Level 2 multiverse extends beyond level 1 by varying fundamental physics, not just initial conditions. Level I varies how matter arranges within fixed physical laws, different galaxies, planets, and histories, but identical standard model everywhere. Level 2 varies the laws themselves, different particles, forces, dimensions, and constants in different bubbles. This creates genuine multiverse of different realities rather than different regions within single reality. The variation is environmental rather than fundamental. Underlying string theory, or M theory, is same everywhere, but vacuum state selection during inflation produces different effective low-energy physics. This is analogous to how waters phase ice, liquid, vapor depends on environmental temperature, though H2O molecules remain identical. Different bubbles are different phases of underlying fundamental theory, with phase determined by how inflation ended in each region. The Level 2 multiverse faces significant conceptual and empirical challenges. The measure problem asks how to assign probabilities across infinite bubbles. Infinitely many bubbles exist with each vacuum state, making probability ratios undefined without choosing measure for counting infinities. Different measures yield contradictory predictions, with no clear principle selecting correct measure. Some measures predict we should observe large cosmological constant, others predict small, some predict we're typical observers, others predict we're atypical. The measure problem remains unsolved despite decades of work, calling into question whether eternal inflation makes coherent, testable predictions. Additionally, testing Level 2 multiverse seems impossible. Other bubbles are forever inaccessible beyond our horizon. Rare bubble collisions might leave CMB signatures, but searches find no convincing collision evidence. Without observational access, Level 2 remains speculation based on theory, rather than empirically confirmed reality. The philosophical implications of Level 2 multiverse are even more radical than Level 1. Not only do all possible histories occur, as in Level 1, but all possible physics occur across bubble ensemble. Every logically consistent vacuum state is realized somewhere. Reality fragments into infinite variations not just of contingent facts, but of necessary seeming laws themselves. The uniformity of physical law, we observe same physics on Earth, Moon, distant galaxies, reflects not fundamental necessity, but environmental accident of our bubble. Constants appearing finely tuned reflect anthropic selection from random distribution. The uniqueness of our universe dissolves into vast landscape where we occupy one unremarkable bubble among infinite physics variants. This challenges essentialism about laws, the idea that physical laws are metaphysically necessary rather than contingent. Level 2 suggests laws are environmental variables varying across multiverse, with only underlying string, M theory being truly fundamental. The edge of reality extends beyond our observable universe into infinite bubble multiverse, with every possible low-energy physics realized somewhere in the eternally inflating expanse. Multiverse Level 2, Many Worlds Quantum. Everett's many worlds interpretation eliminates wave function collapse entirely, all quantum measurement outcomes occur in branching parallel realities, rather than one outcome being randomly selected from possibilities. When Schrödinger's cat is observed, the universe doesn't collapse to either a live or dead state. Instead, it splits into two branches, one containing a live cat and observer who measured alive, another containing dead cat and observer who measured dead. Both outcomes are equally real, occurring in causally disconnected branches that decohere and stop interfering with each other. The wave function never collapses, but continues evolving, according to Schrödinger's equation, deterministically, with apparent randomness arising from observers' subjective uncertainty about which branch they will experience. From global perspective, all branches exist. From within any branch, only that branch is experienced, creating illusion of wave function collapse when it's actually branching. Each quantum measurement splits the universe into multiple copies, exploring different results. Every electron position measurement branches universe into continuum of possibilities, corresponding to wave functions' probability amplitudes at different locations. Every particle decay branches into decayed and not decayed states. Every quantum coin flip branches into heads and tails. The branching is continuous, and pervasive quantum events occur constantly at atomic and subatomic scales throughout the universe, each creating new branches. Within fractions of a second, universe branches into incomprehensibly many nearly identical copies, differing only in microscopic quantum outcomes. Over longer times, these microscopic differences accumulate into macroscopic divergences, branches where you made different choices, where different random mutations occurred, where quantum tunneling produced different outcomes affecting weather, evolution, or technological development. Schrödinger's cat is simultaneously alive in one branch and dead in another. Both outcomes are equally real, from God's eye view encompassing entire wave function. Before the box is opened, the system is in superposition of alive and dead states. When the box opens, observer becomes entangled with cat observer. In one branch measures a live cat, while observer in another branch measures dead cat. The two observers are now in separate branches, each experiencing definite outcome and seeing wave function collapse. Though globally, the wave function contains both branches in superposition. Neither branch is privileged or more real, both exist with equal ontological status. The alive cat branch continues with that observer's memories and experiences, while dead cat branch continues independently with different memories and experiences. From internal perspective, each observer sees unique outcome and doesn't access other branches. From external perspective, both branches exist in quantum superposition. Every quantum event creates branching, generating infinite parallel histories containing all possible pasts and futures allowed by quantum mechanics. The universe's wave function contains all possible configurations of particles weighted by quantum amplitudes, with evolution creating ever more complex superpositions as interactions entangle systems. What we perceive as unique definite history is single thread through vast branching tree. Our conscious experience traces one path, while all alternative paths are equally real in other branches. Quantum indeterminacy isn't destroyed by measurement, but preserved through branching. Both outcomes occur, just in different branches. This means quantum randomness is subjective rather than objective globally. Evolution is deterministic via Schrödinger's equation. Only from within branch perspective does randomness appear, because observer doesn't know which branch they'll experience until after branching. You exist in quantum superposition across countless branches, an infinite ensemble of nearly identical copies differing in quantum measurement outcomes. Most branches are virtually indistinguishable from each other, differing only in which particular atom decayed or which specific photon took which path. Some branches diverge more significantly due to quantum events affecting macroscopic outcomes, mutations, causing different evolutionary paths, quantum tunneling changing chemical reactions, random neural noise affecting decisions. Your consciousness experiences single thread through this branching tree, each moment selecting one branch among many possibilities, though selecting is misleading because all branches occur and contain versions of you continuing their experiences. Whether these branches contain the same continuing consciousness or separate consciousnesses remains philosophically debated. Personal identity across branches challenges conventional notions of self. Level 3 multiverse is implicit in quantum mechanics if wave function collapse is rejected and Schrödinger's equation applied globally without additional collapse postulate. Standard quantum mechanics has two evolution rules: unitary deterministic evolution via Schrödinger's equation between measurements and non-unitary random collapse during measurements. Many worlds eliminates collapse, keeping only Schrödinger's equation, making theory simpler and more elegant. All apparent collapse and randomness emerge from decoherence entanglement with environment rapidly spreading quantum coherence across huge numbers of particles, making interference between branches practically unobservable. Decoherence explains why we don't observe macroscopic superpositions without requiring mysterious collapse mechanism. Many worlds requires no additional physics beyond standard quantum formalism. Applied consistently, it's minimalist interpretation, adding nothing to formalism but removing collapse postulate. The conceptual challenges are profound. How do we interpret probability if all outcomes occur? Probability in many worlds reflects subjective uncertainty about which branch you'll experience, analogous to uncertainty about your location when multiple identical copies exist in level 1 multiverse. Before measurement, you're in superposition across branches. After measurement, there's no fact about which branch you are in because you're in all of them, each experiencing different outcome. What you subjectively observe depends on which branch your consciousness thread continues through, with probabilities given by Born rule squared amplitudes. Why Born rule holds in many worlds remains debated, with various derivations attempting to show it emerges from rational decision theory or information theoretic considerations. The ontological cost of many worlds is extraordinary. It multiplies entities beyond anything other interpretations require. Each quantum event spawns entire new universes, creating unimaginable proliferation of parallel realities. Critics argue this violates Occam's razor, despite many worlds' mathematical simplicity. Proponents counter that Occam's razor favors theoretical simplicity rather than ontological parsimony. Many worlds has simplest laws, just Schrödinger's equation, despite maximal ontology, infinite branches. The trade-off between theoretical elegance and ontological extravagance remains philosophically contested. Additionally, many worlds might be empirically indistinguishable from Copenhagen interpretation. Both make identical predictions for all observations, differing only in unobservable claims about unmeasured systems. This makes choosing between interpretations matter of philosophical preference rather than empirical test. The level 3 multiverse suggests reality is quantum wave function containing all possible histories in superposition, with our experience being single decohered branch among infinite others. Free will becomes compatible with determinism globally, wave function evolves deterministically, but subjectively we experience branching where both choices occur in different branches, creating sense of genuine alternatives. Death loses finality if consciousness continues in surviving branches. Anthropic selection might mean we always experience branches where we survive quantum probabilistic events. The edge of reality includes all quantum branches simultaneously, with experienced reality being narrow slice through quantum possibility space. Many worlds transforms understanding of actuality. What is real includes not just what we observe, but all quantum mechanically possible alternatives existing in parallel decoherent branches, constituting complete quantum reality's vastness beyond direct experience. Multiverse level I-Fi mathematical structures. Tegmark's ultimate ensemble proposes the most radical multiverse hypothesis. All mathematical structures exist physically. Every self-consistent mathematical structure corresponds to a real universe somewhere in ultimate reality. This extends the multiverse concept to maximum generality. Level I varies initial conditions within our physics. Level 2 varies physical constants and forces. Level 3 varies quantum measurement outcomes. But Level 4 varies the mathematical structure itself, different geometries, different dimensionalities, different algebraic systems, different logical frameworks. Some universes have 3 spatial dimensions, others have 17. Some have time, others are timeless. Some have continuous spacetime, others discrete. Some have quantum mechanics, others pure classical physics or entirely different frameworks. Every mathematical possibility is physically realized somewhere in the ultimate ensemble. Different mathematics means profoundly different physics, spacetime, and reality structures. In universes governed by non-Euclidean geometry, parallel lines might converge or diverge. Triangles have angle sums different from 180 degrees, and spatial relationships follow unfamiliar rules. In universes with different dimensionality, beings experience space utterly differently. 2-dimensional beings confined to surfaces, 4-dimensional beings perceiving all of our 3-dimensional space simultaneously. In universes with different algebraic structures, addition and multiplication might not commute, linearity might fail, or mathematical relationships we consider fundamental might not hold. In universes with different logic, perhaps paraconsistent logic, allowing contradictions or intuitionistic logic without excluded middle truth and falsity, have different meanings. The diversity is limited only by mathematical consistency. Any self-consistent formal system corresponds to possible universe. We inhabit one mathematical structure among all logically possible universes. Specifically, the mathematical structure describing spacetime as 4-dimensional pseudo-Riemannian manifold with metric signature plus or plus plus plus, governed by Einstein's field equations, with matter and forces described by quantum field theories with specific gauge groups and particle content. This particular structure is just one among infinite mathematical possibilities. Why do we observe this specific structure rather than another? Tegmark proposes no answer. All structures exist equally, and we necessarily observe one compatible with conscious observers existing. Most mathematical structures probably don't support complexity, computation, or consciousness, making them unobservable by definition. We observe this structure because it permits observers, not because it's privileged or unique. This extends multiverse maximally. Level 1 varies initial conditions by exploring different regions of infinite space. Level 2 varies physical constants by exploring different string theory vacuum states. Level 3 varies quantum outcomes by exploring all branches of wave function. And Level 4 varies mathematics itself by exploring all self-consistent formal structures. Each level contains all lower levels. As subsets, Level 2 contains infinite Level 1 multiverses in each bubble. Level 3 contains infinite Level 2 landscapes in each quantum branch. Level 4 contains infinite Level 3 wave functions in each mathematical structure. The hierarchy becomes vertigo-inducing. Our observable universe is one region in infinite Level 1 space, in one bubble in Level 2 landscape, in one quantum branch in Level 3 wave function, instantiating one mathematical structure in Level 4 ultimate ensemble. Our reality is nested infinitely deep, in multiverses within multiverses within multiverses. Mathematical democracy holds that no mathematical structure is privileged all exist equally by virtue of mathematical consistency alone. There's no meta-law selecting which structures are real versus merely possible. Existence isn't special property conferred by some external criterion, but follows automatically from mathematical coherence. This is mathematical Platonism. Taken literally, mathematical objects don't merely exist abstractly in timeless realm of forms, but constitute physical reality directly. The physical universe is mathematical structure, and all mathematical structures are physical universes. This dissolves the mystery of why mathematics describes physics so effectively. Physics is mathematics, mathematical relationships are physical laws, and apparent difference between abstract math and concrete physics is illusory. Eugene Wigner's famous essay on the unreasonable effectiveness of mathematics in natural sciences is explained. Mathematics is effective because reality is mathematical. Physical reality equals mathematical structure. In Tegmark's view, there's no distinction between mathematical models and physical stuff. What we call matter, energy, fields, and space-time are relationships in mathematical structure, not substances existing independently of mathematics. An electron isn't a tiny particle made of some non-mathematical stuff, but rather a pattern in quantum field configuration describable entirely by mathematical equations. Space-time isn't a container made of some spatial substrate, but geometric structure defined purely by metric tensor relationships. Consciousness might be information processing pattern in mathematical structure, permitting self-reflective computation. Everything reduces to mathematics. No physical ontology beyond mathematical relationships exists. This is radical structural realism, where only structure is real, with apparent substance being emergent description of mathematical patterns. Existence equals mathematical consistency in this framework. A universe exists if and only if its governing mathematical structure is self-consistent without contradictions. Consistency is the only criterion for reality. This makes existence vast beyond imagination. Every consistent formal system corresponds to existing universe, and formal systems are unimaginably diverse. The ultimate ensemble contains not only all physically reasonable universes with different constants or dimensions, but all mathematically possible universes, including those with bizarre, incomprehensible structures bearing no resemblance to anything we'd recognize as physics. Most universes are probably simple, random cellular automata, trivial algebraic systems, formless mathematical spaces. Our universe is unusual for permitting complex structures like galaxies, stars, and observers. This is the most speculative multiverse level, blurring boundaries between physics and mathematics, and suggesting ultimate reality transcends space-time entirely, consisting of abstract mathematical relationships without physical instantiation. We don't live in mathematical model of universe, we live in mathematical structure itself, with physical appearance being how mathematical structure appears to conscious subsystems within it, experiencing time, space, and matter emergently. The ultimate ensemble dissolves traditional ontological questions. Why do physical laws have their form? Because they're one mathematical structure among all possible structures. Why does anything exist? Because mathematical consistency guarantees existence. What existed before the Big Bang? The question presupposes time. But time is feature of specific mathematical structure. Other structures are timeless, and ultimate ensemble transcends time entirely. The philosophical implications are staggering. If all mathematical structures exist, then reality is everything logically possible, bounded only by logical consistency, not by any selective principle, choosing which possibilities actualize. There's no creation event, because mathematical structures exist necessarily and eternally. There's no fine-tuning mystery, because all possible constants are realized across structures. There's no anthropic coincidence, because we necessarily inhabit one structure among infinite possibilities supporting observers. The edge of reality becomes the edge of mathematics itself, the boundary between consistent and inconsistent formal systems. Beyond that edge lies not unactualized possibilities, but logical impossibilities, contradictory systems that cannot exist even in ultimate ensemble. The edge of reality is the edge of coherence, where logic itself breaks down and existence becomes undefined. This is ultimate boundary, not physical horizon or quantum uncertainty or conscious limits, but logical necessity beyond which nothing, not even abstract mathematics, can extend. Time as illusion, the block universe. Special relativity's relativity of simultaneity, the fact that different observers in relative motion disagree on which events are simultaneous, directly implies the block universe where past, present, and future exist equally in four-dimensional space-time, rather than only the present moment existing. According to special relativity, there is no universal present moment. What is now for you is different from what is now for someone moving relative to you. Events simultaneous in your reference frame are not simultaneous in theirs. More dramatically, events in your future can be in someone else's past if they're moving sufficiently fast. If different observers cannot even agree on which events have already happened versus are yet to happen, then temporal ordering cannot be an objective feature of reality. Instead, all events past, present, and future from any perspective must exist equally in the four-dimensional space-time manifold, with different observers simply slicing this manifold along different planes of simultaneity. Space-time is four-dimensional structure, with time as a dimension alongside three spatial dimensions not separate from space but unified into single geometric entity. In Minkowski spacetime, events are located by four coordinates t, x, y, z, with metric defining distances combining temporal and spatial separations. ds squared equals c squared dt squared plus dx squared plus dy squared plus dz squared. Time differs from space through the metric signature negative for time component, positive for space, but is otherwise formally similar as a dimension. The universe is not three-dimensional space evolving through time, but four-dimensional space-time existing as complete unchanging structure. Past, present, and future are slices through this four-dimensional manifold, analogous to how here and there are different locations in three-dimensional space. Just as all spatial locations exist simultaneously, there is no privileged spatial location that is real, while others are not yet real or no longer real. All temporal locations exist simultaneously in the block universe. The present moment is subjective observer perspective, not objective reality feature. When you experience now, you're experiencing one three-dimensional spatial slice through four-dimensional space-time, corresponding to your current proper time, measured by clock you carry. But someone else moving relative to you experiences a different now, a different three-dimensional slice, tilted at angle through space-time depending on their velocity. There is no objective present moment encompassing the entire universe, no cosmic now defining which events exist versus which haven't happened yet or have already passed. The flow of time, the sensation that the present moves from past toward future, is subjective phenomenon arising from consciousness, memory, and thermodynamics arrow, not objective temporal becoming. From God's eye view or block universe perspective, all times exist eternally in timeless four-dimensional structure, with temporal flow being artifact of how conscious observers, embedded within space-time, experience their world lines. All moments exist timelessly in the block. Past events didn't cease existing. Future events already exist. Everything is laid out in eternal four-dimensional structure. Your birth, childhood, career, old age, and death all exist equally as events in spacetime, occupying different temporal coordinates just as different spatial coordinates correspond to different locations. When we say an event is past, we mean it occurs at earlier temporal coordinate along our world line, the path through spacetime traced by our existence. When we say an event is future, we mean later temporal coordinate. But these are perspectival distinctions, like here versus there, in space from a temporal block universe perspective. Past and future events are equally real, differing only in temporal location. The block universe is static and unchanging. Nothing becomes or ceases to be. Everything simply exists at its space-time location eternally. Consciousness moves through the block, experiencing successive nows. Our awareness traces world line through space-time, experiencing events as they occur along our trajectory. This creates subjective illusion of temporal flow and becoming. At each moment of proper time, we experience the present, remember the past, and anticipate the future. But this is perspectival. The present we experience is simply where our consciousness currently is along our world line, not an objective moving present. As our consciousness progresses through time, we experience successive events in our world line, creating sensation of time passing. But from block universe perspective, our entire world line exists simultaneously. All our moments of consciousness exist at once in four-dimensional space-time. The version of you reading this exists at one temporal coordinate. Earlier versions exist at earlier coordinates. Later versions exist at later coordinates, all equally real, all existing eternally in the block. Free will faces serious tension with block universe determinism. If all future events already exist in four-dimensional space-time structure, laid out eternally and unchangeably, how can we be free to choose differently than we will choose? Our decisions, actions, and thoughts are all events in space-time with definite temporal locations. The future is not open set of possibilities, but determinate fixed structure existing just as definitely as the past. If tomorrow's events already exist in the block, how can our choices tomorrow be genuinely free rather than predetermined? Compatibilists argue free will is compatible with determinism. Freedom means acting according to our desires and beliefs without external coercion, not ability to do otherwise. Libertarians insist genuine free will requires open future with multiple possible outcomes, incompatible with block universe. Some appeal to quantum indeterminacy, creating open futures, though quantum many worlds also yields block universe containing all branches deterministically. The eternalism versus presentism debate asks whether all times are equally real or only the present exists. Presentism holds that only present moments exist. Past is no longer real. Future is not yet real. Only the instantaneous present is ontologically real. Eternalism, implied by block universe, holds that all times are equally real. Past, present, and future exist on equal ontological footing. Physics strongly favors eternalism through special relativity's demonstration that simultaneity is relative if no objective present exists for all observers. Presentism fails. General relativity treats time geometrically as dimension, further supporting eternalism. Quantum mechanics presents complications. Some interpretations, like many worlds, support block universe, while collapse interpretations might favor presentism, where wave function collapse creates objective becoming. Nevertheless, most physicists accept eternalism based on relativity's implications. Block universe suggests the edge of reality includes all of time past and future are as real as present, with temporal boundaries being complete extent of space-time from Big Bang to ultimate fate. If space-time is finite in temporal extent from initial singularity to final heat death or Big Rip, then block universe is bounded four-dimensional structure with all events, from beginning to end, existing eternally. If time is infinite in some direction, block universe extends infinitely without temporal edges. Either way, reality encompasses all time, not just the fleeting present. This transforms understanding of existence. You don't merely exist now, but exist eternally at your space-time location. You are four-dimensional structure extended through time, a space-time worm persisting from birth to death as unified entity. Death doesn't end existence, but marks temporal boundary of four-dimensional world line. You continue existing eternally at earlier temporal coordinates. The past isn't gone, but remains eternally real. The future isn't yet to come, but already exists. Time's edge is reality's temporal extent, and we exist across that entire extent as four-dimensional beings experiencing our world lines from within, through successive moments of consciousness, creating illusion of temporal flow through eternal unchanging block. Consciousness beyond the brain. The hard problem of consciousness, articulated most clearly by philosopher David Chalmers, questions whether consciousness can arise from purely physical processes or requires something beyond materialism. Neuroscience can explain how brain processes information, correlate neural activity with behavioral responses, and map brain regions responsible for perception, memory, and decision-making. These are the easy problems. Though technically challenging, they're straightforward in principle because they involve explaining functions and behaviors through mechanisms. But the hard problem asks why these physical processes have associated subjective phenomenal experience, why there is something it is like to see red, feel pain, or taste coffee rather than information processing occurring unconsciously in philosophical zombie. Science explains the physical correlates and functional roles of consciousness, but seemingly cannot bridge the explanatory gap to subjective quality, why certain patterns of neural firing feel like anything from the inside. Panpsychism proposes consciousness is fundamental property of matter at all levels, not just complex brains, but even elementary particles have primitive awareness or proto-consciousness. Electrons don't have human-like thoughts or perceptions, but possess minimal experiential quality that combines in specific configurations to create complex consciousness. Complex brains have rich integrated consciousness because billions of neurons, each with micro-consciousness, aggregate into unified field through integration. Panpsychism solves the hard problem by denying that consciousness emerges from non-conscious matter. Instead, consciousness is always present, with complexity determining richness rather than presence. Objections include combination problem. How do micro-consciousnesses of particles combine into unified macro-consciousness of brain, and implausibility that thermostats and electrons are conscious? Yet panpsychism attracts serious philosophical attention as potentially solving consciousness's origin mystery by making it fundamental rather than emergent. Idealism inverts materialism's priority. Consciousness is fundamental, and matter is derivative mental construct rather than consciousness emerging from material brain. In idealism, physical world exists as experiential content. Reality is ultimately mental, with apparent material objects being patterns in universal consciousness or phenomenal experiences rather than mind-independent substances. Berkeley's subjective idealism held that objects exist only as perceptions in minds, with God's mind ensuring consistency across individual experiences. Contemporary idealism suggests material world is appearance that consciousness takes when viewed from particular perspective, with underlying reality being experiential or mental rather than physical. This avoids hard problem entirely by denying that consciousness arises from non-conscious matter. Matter never existed as separate substance, but was always manifest consciousness. Critics object that idealism fails to explain detailed neurological correlations. Why does brain damage affect consciousness if mind is more fundamental than matter? Near-death experiences report awareness during clinical death with no detectable brain activity, suggesting consciousness might exist independent of brain function. Patients describe floating above operating tables, watching surgeries, traveling through tunnels toward light, encountering deceased relatives, experiencing life reviews, and returning with transformed perspectives. Some report accurate perceptions of events occurring while clinically dead, seeing objects on high shelves, overhearing conversations in different rooms. Skeptics attribute these to residual brain activity, misidentified as cessation, memories created during resuscitation, or psychological construction. But some cases involve verified perceptions seemingly impossible without consciousness during periods of flat EEG and cardiac arrest, when brain receives no oxygen or blood flow. If genuine, such cases suggest consciousness can exist independent of functioning brain, either surviving death or produced by non-brain mechanisms. Alternative explanations invoke quantum consciousness in microtubules surviving brief periods without neural activity, or consciousness as non-local field interacting with brain rather than product of brain. Terminal lucidity shows dementia patients gaining sudden clarity and lucidity shortly before death, despite severe brain damage that previously prevented coherent thought. Patients with advanced Alzheimer's, massive strokes, or brain tumors destroying cognitive capacity sometimes experience brief windows of restored consciousness, recognizing family members, speaking coherently, and displaying personality before dying hours or days later. This puzzles neuroscience. If consciousness requires intact neural networks and destroyed neurons cannot function, how do damaged brains temporarily produce normal consciousness? Possible explanations include final metabolic crisis temporarily enhancing remaining neural activity, reduction in inhibitory processes unmasking preserved function, or consciousness accessing brain through non-physical means that brain damage normally blocks, but death approach allows. Terminal lucidity challenges strict brain equals mind materialism by demonstrating consciousness apparently independent of intact neural substrate. Quantum consciousness theories propose mind involves quantum coherence, superposition, and entanglement, allowing consciousness to integrate information beyond classical neuron networks. Penrose-Hameroff orchestrated objective reduction theory suggests microtubules inside neurons maintain quantum states long enough for quantum computation to occur, with consciousness arising from orchestrated collapses of quantum wave functions when gravitational differences between superposed states reach threshold. Quantum coherence would allow integration across brain regions faster and more completely than classical signaling permits, potentially explaining consciousness's unity and binding. Critics argue biological environments are too warm and noisy for quantum coherence. Decoherence would destroy quantum states in femtoseconds, far too quickly for neural computation. However, recent discoveries of quantum effects in photosynthesis and avian magnetoreception suggest biology might harness quantum phenomena more effectively than previously thought. If consciousness involves quantum processes, it might connect to quantum foundations of reality itself, rather than being merely emergent property of classical neural circuits. If consciousness transcends physical substrate, existing beyond specific neural implementations, it might exist in higher dimensions, inaccessible to normal observation, as pure information pattern that can instantiate in different substrates, including biological brains and potentially computers or quantum fields, or as fundamental feature of reality itself, woven into universe's fabric rather than emergent epiphenomenon. Higher dimensional theories suggest consciousness's unity and non-locality might result from connections through extra dimensions collapsed at everyday scales, but accessible to consciousness. Information theoretic approaches view consciousness as integrated information pattern, substrate independent in principle. The same consciousness could exist in biological neurons, silicon chips, or exotic quantum substrates. Panpsychism makes consciousness fundamental property present at all scales, with complex brains exhibiting rich consciousness because they integrate vast information rather than consciousness emerging de novo from non-conscious components. These possibilities suggest consciousness existing beyond brain, beyond body, perhaps beyond space-time, at reality's deepest edge, where subjective experience and physical law meet and merge. If consciousness is fundamental rather than derivative, the universe might be intrinsically experiential, with physical laws describing structural relationships within universal consciousness, rather than consciousness being occasional accident in predominantly non-conscious universe. The edge of reality would then include not just physical cosmos, but vast experiential landscape, the total space of possible conscious experiences and phenomenal qualities. Consciousness would not be trapped inside skulls, but woven throughout reality, potentially existing in forms we cannot imagine across multiverse levels and mathematical structures. The mystery of consciousness might not be explained by reducing it to physical mechanisms, but by recognizing it as irreducible aspect of reality, co-equal with matter, energy, space, and time, the inside perspective complementing outside perspective, subjective experience balancing objective description, mental accompanying physical as dual aspects of unified reality beyond the edge where comprehension meets wonder and science meets mystery. The simulation within simulations. Nested simulations propose that simulations can run simulations recursively, creating infinite hierarchy where determining base reality becomes impossible. If advanced civilizations create simulations containing conscious beings, and those simulated beings eventually develop technology to run their own simulations, then simulations within simulations cascade downward through levels. Each level believes itself potentially real while being simulation for the level above and running simulations for levels below. This creates epistemic vertigo. How many levels deep are we? Is there even a base reality, or do simulations extend infinitely? The computational requirements grow exponentially. Simulating a universe requires vast resources. Simulating that universe, simulating another universe, requires even more. But if simulations optimize by rendering only observed details and compressing unobserved regions, nested simulations might be feasible for sufficiently advanced civilizations exploiting computational shortcuts. Infinite regression emerges naturally from nested simulation hypothesis. Each simulated civilization creates its own simulations ad infinitum. If this occurs, then base reality is either unreachable, buried beneath infinite simulation layers, or doesn't exist with simulations extending infinitely without foundation. This parallels cosmological questions about infinite regress in causation. What caused the Big Bang? What caused that cause, extending infinitely? Some argue infinite regress is impossible, requiring foundational base reality. Others accept infinite chains as logically coherent, citing mathematical infinities as precedent. If simulations nest infinitely, the concept of real versus simulated loses, meaning all levels are equally real to inhabitants, equally simulated from external perspective. Reality becomes relative rather than absolute. Real for you is whatever level you inhabit, with no privileged ground truth accessible from any position within the hierarchy. Computational limits constrain nested simulations through the Bekenstein bound and holographic principle. The Bekenstein bound limits information content in any spatial region maximum entropy equals 1/4 the area in Planck units. For the observable universe, with horizon area 10 to the 123rd Planck areas, maximum information is 10 to the 123rd bits. Simulating this information exactly requires at least equal computational resources, leaving insufficient capacity for higher-level reality to run our simulation, plus everything else. However, lossy compression and approximations reduce requirements dramatically. The holographic principle suggests three-dimensional physics is encoded on two-dimensional boundaries, potentially enabling efficient simulation through boundary computation rather than volumetric. Quantum computers might simulate quantum systems efficiently through natural quantum parallelism, with sufficient cleverness rendering only observed details using procedural generation for unobserved regions. Exploiting physical symmetries for compression-nested simulations might be computationally tractable despite apparent resource limits. Ancestor simulations, as proposed by Bostrom, specifically simulate civilizations' evolutionary history to study or recreate ancestors. Posthuman civilizations might run countless ancestor simulations exploring counterfactual histories. What if Rome didn't fall? What if Industrial Revolution occurred earlier? What if different evolutionary paths were taken? These simulations would contain conscious beings experiencing lives indistinguishable from base reality, believing themselves historically real. If ancestor simulations are common, then most conscious observers at our technological level are simulated rather than original, because each advanced civilization runs many simulations containing billions of simulated people. This creates Bostrom's trilemma. Either civilizations go extinct before running ancestor simulations, choose not to, despite capability, or we are almost certainly simulated. Nested ancestor simulations compound this simulated civilizations, eventually run their own ancestor simulations, creating simulation genealogies where most beings are multiple simulation levels removed from base reality. Substrate independence is the hypothesis that consciousness doesn't require biological neurons but can exist on any substrate implementing appropriate information processing silicon chips, quantum computers, or exotic computational media. If substrate independence holds, then consciousness is pattern rather than substance, algorithm rather than wetware. Uploading minds to digital substrates becomes possible in principle scanning brain states and recreating information processing patterns in computer hardware. The uploaded mind would subjectively be the same person continued in new medium, though philosophical questions arise about identity, continuity, and whether upload is continuation or copy. Substrate independence makes simulation hypothesis plausible. Simulated beings could be genuinely conscious despite running on computer hardware, experiencing subjective reality equally real to them as our experience is to us. It also enables mind transfer across simulation levels, uploading out of simulation into higher reality, or downloading minds from higher reality into simulations. The question of whether we are NPCs, non-player characters, with scripted behaviors, or player characters with genuine agency and consciousness divides simulation scenarios. In video game terminology, NPCs are automated characters controlled by algorithms displaying convincing behaviors without subjective experience, while player characters are avatars controlled by conscious players. If we're in simulation, are we philosophical zombies executing programs without real awareness, or are we genuinely conscious? The question might be meaningless. If consciousness is computational pattern complex, enough information processing produces consciousness regardless of substrate, making no fundamental distinction between real brains and simulated ones. Alternatively, only some simulated beings might be conscious, Perhaps only main characters receive conscious instantiation, while background characters run on autopilot. We assume we're conscious through direct, subjective experience, but cannot verify whether others are conscious or NPCs. The hard problem of consciousness prevents distinguishing from outside. Escaping simulation raises intriguing possibilities explored in science fiction. If we detect we're simulated, could we exploit simulation mechanics like video game glitches to escape? Might quantum tunneling, entanglement, or other quantum weirdness represent exploitable bugs in the simulation code? Could we communicate with simulators through contrived quantum states or messages encoded in fundamental constants? Or hack our way out by achieving sufficient computational sophistication to bootstrap into higher reality? These scenarios are fascinating, but likely fantasy. Any escape attempts would presumably be anticipated and blocked by simulators. Moreover, escaping to higher reality might simply reveal another simulation layer. The only true escape would be reaching base reality, which might be impossible if simulations nest infinitely or if base reality is radically different from simulated ones, making survival there impossible. Even if escape succeeds, the escapee faces existential crisis. Everything they knew is revealed as simulation, their entire world shown to be fiction, relationships revealed as programmed NPCs. Base reality in nested simulation scenarios might have radically different physics, dimensionality, or even temporal structure than simulated realities. If our universe is optimized simulation running on computational substrate, base reality might not have three spatial dimensions, continuous time, or particle physics resembling ours. It might be pure information processing with no spatial extension, or 12-dimensional with exotic forces we cannot imagine. Consciousness in base reality might experience existence completely differently. No linear time, no localized sense of self, no sensory perception. Alternatively, base reality might be simpler than simulations, perhaps two-dimensional or governed by cellular automaton rules, much simpler than our physics. The simulators themselves might be incomprehensible to us, as incomprehensible as humans are to simulated characters in our video games who lack concepts for keyboards, screens, or players. Reaching base reality might be enlightenment revealing ultimate truth, or horror discovering existence's foundation is nothing like imagined, or impossible because base reality's physics cannot support consciousness structures from simulated realities. Conscious reality creation. John Wheeler's participatory universe proposal suggests observers actively participate in creating reality rather than passively observing pre-existing world. Wheeler argued that quantum mechanics reveals reality, emerges through observation. The universe is participatory, requiring conscious observers to actualize possibilities into facts. His famous diagram shows the universe as self-excited circuit where observers emerge from physical law, then observations actualize the physical law that created observers, forming strange loop. The delayed choice quantum eraser demonstrates this participatory aspect. Measurements now affect past behavior, suggesting the past isn't fixed until observed. Wheeler proposed the universe's entire history might be retroactively determined by present observations. The act of observing early universe through telescopes actualizes cosmic history that produced us. This radical view makes consciousness fundamental to reality rather than incidental byproduct, suggesting reality is co-created through observation. Consciousness collapsing quantum possibilities into actuality represents strongest form of observer-created reality. If consciousness causes wave function collapse, then conscious observation literally creates definite reality from quantum superposition's possibilities. Before observation, particles exist in liminal state between existence and non-existence, present as potentials, not actualities. Observation actualizes specific outcome from possibility space, making real what was merely potential. This interpretation makes consciousness ontologically fundamental. Physical reality cannot exist fully without conscious observation to collapse quantum states. The universe before consciousness would be vastly underdetermined sea of superposed possibilities, crystallizing into definite history only when consciousness emerges and observes backward in time. This view is minority position in physics, but finds support in quantum foundations. Research suggesting standard interpretations face serious problems that consciousness might resolve. Delayed choice quantum eraser experiments, where measurements occur after particles pass through slits yet determine whether interference appears, demonstrate apparent retrocausality. Future measurements affecting past behavior. Standard quantum mechanics explains this through timeless correlation without literal backward causation, but participatory interpretation suggests present measurements retroactively actualize past events. When we measure which path information, we actualize past where particle took definite path. When we erase which path information, we actualize past where particle went through both slits. The past is not fixed, but determined by present observations. This extends to cosmic scales in Wheeler's vision. Our observations of ancient starlight now might actualize billions of years ago events that produced the photons, suggesting cosmic history is being written retroactively through present observations. Retrocausality, where future events influence past outcomes, appears in certain interpretations of quantum mechanics, including two-state vector formalism and transactional interpretation. These models propose quantum states evolve both forward and backward in time, with final states constraining past states just as initial states constrain future. Measurements select consistent histories, threading between past and future constraints. This time-symmetric view dissolves apparent paradoxes in delayed choice experiments. Future and past co-determine present without contradictions, because quantum mechanics is fundamentally time-symmetric, with apparent time asymmetry emerging from thermodynamics and decoherence. Retrocausality doesn't enable sending messages to the past or creating paradoxes, but does suggest future and past are mutually dependent, rather than past uniquely determining future. If retrocausality operates, then present consciousness might indeed affect past retroactively, co-creating history through observation. The Global Consciousness Project, running since 1998, monitors random number generators worldwide, searching for correlations during major global events, disasters, celebrations, collective attention moments. The hypothesis is that coherent mass consciousness affects random quantum processes, creating detectable statistical deviations during events drawing billions of people's attention simultaneously. Results show marginal statistical correlations during events like September 11 attacks, royal weddings, and New Year celebrations, though effects are small and controversial. Skeptics argue for selection bias, multiple comparison problems, and random fluctuations. Proponents contend that even small effects suggest consciousness interacts with quantum randomness. If consciousness affects random number generators, it implies mind-matter interaction, where observation or intention influences physical systems. This would be weak form of conscious reality creation, not creating reality wholesale, but slightly biasing probabilities through mental focus. Placebo effects demonstrate belief's power to change physical reality. Patients improve when receiving inert treatments they believe are effective. Extensive medical research confirms placebo responses are real physiological changes, not merely subjective reports. Placebo analgesia activates endogenous opioid systems, reducing pain through measurable brain mechanisms. Placebo antidepressants produce neurochemical changes similar to actual drugs. Nocebo effects show negative expectations producing physical harm. Patients warned of side effects experienced them despite receiving inert substances. The mechanism appears to be expectation-driven neuroplasticity, and unconscious conditioning, rather than magical belief, creates reality. But placebo effects demonstrate consciousness profoundly influences physiology. Some interpret this as evidence for consciousness affecting matter belief, literally reshaping physical body. Skeptics note placebo operates through known biological mechanisms rather than quantum consciousness or paranormal channels, though the power of belief remains striking. Prayer and meditation studies, investigating whether focused intention affects material reality, have produced controversial results. Studies examining prayer's effects on healing find mixed results. Some show small benefits, others show null effects. Most face methodological challenges, including lack of blinding and selective reporting. Distant healing intentions show no reliable effects in well-controlled studies. Meditation research demonstrates robust changes in brain structure and function. Experienced meditators show increased cortical thickness, altered default mode network activity, and improved emotional regulation. These are neuroplastic changes rather than consciousness affecting external reality. Though some meditation traditions claim abilities to influence external events through focused consciousness, laboratory studies of meditation's effects on random number generators or quantum systems show null or marginally significant results, insufficient to establish genuine effects. The preponderance of evidence suggests consciousness powerfully affects its neural substrate, but doesn't influence external physical systems except through conventional causal chains involving bodily action. Whether we create reality through observation or intention remains open question bridging physics, philosophy, and mysticism. Quantum mechanics definitely shows observation affects outcomes, measurement determines which properties actualize from possibilities. Whether this requires consciousness or merely physical interaction remains debated. The evidence for consciousness directly influencing external physical systems through intention alone, psychokinesis, prayer affecting distant events, meditation influencing quantum randomness, is weak and controversial, with most well-controlled studies finding null results. Yet placebo effects demonstrate belief's power over bodily states. Quantum mechanics shows observation's foundational role in determining outcomes, and participatory anthropic principle suggests observers might be essential to actualizing reality. The edge between observer and observed blurs in quantum domain. Whether this means consciousness creates reality, or reality creates consciousness, or both emerge together in participatory loop, remains one of existence's deepest mysteries, straddling the edge where science meets metaphysics and experience meets explanation. Beyond comprehension, unknowable reality. Gödel's incompleteness theorems, proven by Kurt Gödel in 1931, demonstrate that any sufficiently complex formal system contains true statements that cannot be proven within the system. Mathematics itself has limits. Arithmetically true propositions exist that no proof can establish from axioms. This reveals fundamental limits to formal reasoning. Complete systems are inconsistent, consistent systems are incomplete. Some mathematical truths are knowable only through intuition or axioms beyond the formal system. If mathematics has inherent limits, then physics described mathematically inherits those limits. Some physical truths might be unprovable, some questions unanswerable within any theoretical framework we can construct. Reality might contain aspects forever beyond formal description, truths inaccessible to mathematical physics, phenomena that cannot be captured in equations. The incompleteness theorems suggest the edge of reality includes unknowable truths beyond reach of logic and mathematics. The limits of formal systems, mathematics and logic constrain what can be known through scientific method. Science proceeds through observation, hypothesis, mathematical modeling, and experimental testing. But Gödel shows mathematics is inherently incomplete some truths are unprovable. Heisenberg shows observation is limited by quantum uncertainty. Some properties cannot be measured simultaneously. Horizons show observation is limited by causality. Some regions are forever inaccessible. These limits are fundamental, not technical. No amount of scientific progress can overcome them because they're woven into logic, quantum mechanics, and space-time structure. Science's domain is the empirically accessible, mathematically describable, and logically provable. Beyond these boundaries lies what we might call metaphysics, mysticism, or simply mystery aspects of existence that transcend scientific methods' reach, not because science hasn't developed enough, but because these aspects lie outside science's fundamental scope. Phenomena forever beyond the scientific method include questions about consciousness's subjective quality, why experiences feel like something rather than processing, without awareness, the origin of existence itself, why something exists rather than nothing, and the nature of base reality if we're in nested simulations. Science can correlate brain states with conscious experiences, but cannot explain why correlation exists, why certain information processing patterns have associated phenomenal experience. Science can trace cosmic evolution back to Big Bang, but cannot address what preceded it, or why laws of physics have their particular form. Science can posit simulation hypothesis, but cannot prove or disprove it. Simulations can mimic reality perfectly by construction. These questions might be inherently beyond empirical investigation, requiring philosophical or mystical approaches, or they might be meaningless, asking what's north of the North Pole. The distinction between genuinely unknowable and merely currently unknown remains unclear. The question of what existed before the Big Bang, or before space-time, encounters fundamental conceptual barriers. General relativity describes space-time as dynamic entity that began at Big Bang singularity 13.8 billion years ago. Asking what happened before the Big Bang assumes time extended earlier than Big Bang, but time itself began with space-time. The question might be meaningless, like asking what's north of the North Pole. There is no time before time began, no space beyond space's edge. Alternatively, quantum gravity theories suggest pre-Big Bang epochs, eternal inflation where our Big Bang was bubble nucleation in larger inflating space, cyclic cosmologies where universes expand and contract repeatedly, or quantum cosmology where a universe tunneled from nothing via quantum fluctuation. But these theories remain speculative without empirical evidence, and they push the question back: what existed before eternal inflation? What powers cyclic repetition? What is the nothing from which quantum fluctuation arose? Why something rather than nothing? This question, articulated by Leibniz and debated by philosophers for centuries, asks why existence itself exists. Clearly, something exists. We observe a universe with matter, energy, forces, and structure. But why? Why not absolute nothingness? No space, time, matter, energy, consciousness, or possibilities. Proposed answers include: something is simpler than nothing, because nothing requires specifying and maintaining absence, while something requires no justification. Quantum mechanics allows fluctuations from vacuum creating universes. God, or necessary being, exists by definition, requiring no cause. All mathematical structures exist necessarily because mathematical truths are eternal and uncaused, or the question is meaningless because existence is logically prior to causation, making why exists incoherent. None of these answers fully satisfy, suggesting the question might transcend human comprehension. Our minds evolved to understand medium-sized objects and social dynamics, not ultimate existence questions. The fine-tuning problem notes that fundamental physical constants appear precisely calibrated for complexity, structure, and life. The cosmological constant is fine-tuned to 120 decimal places. If larger by tiny amount, universe would have expanded too quickly for galaxies to form. If smaller, universe would have recollapsed. The strong nuclear force is fine-tuned to 1%. If stronger, stars would burn too fast. If weaker, stars wouldn't form. Dozens of constants show similar fine-tuning. Explanations include anthropic selection. Infinite multiverse produces all constant combinations. We necessarily observe life-compatible values. Necessity deeper theory predicts these specific values. Or design intelligence deliberately chose constants for specific purpose, including enabling observers. Fine-tuning doesn't prove design, but shows our universe sits on knife edge of possible constants, suggesting either extraordinary luck, vast multiverse making luck inevitable, or underlying principle selecting these values. The anthropic principle observes that we necessarily find ourselves in universe compatible with our existence, regardless of how improbable that universe is. This is weak anthropic principle. Our existence constrains observations we can make. Strong anthropic principle claims universe must have properties, allowing observers to emerge. Observation requires observers, observers require complex chemistry, chemistry requires fine-tuned constants, therefore constants must be fine-tuned. This seems to reverse causation. Did observer requirements cause fine-tuning? Multiverse provides non-teleological explanation. Many universes with random constants exist. Most are sterile, rare, fine-tuned ones produce observers. The anthropic principle applied to simulations suggests simulated beings are more common than base reality beings. If civilizations create many simulations, we should expect to be simulated not because we are, but because most observer moments occur in simulations. The anthropic principle shapes expectations about reality's nature based on fact that we exist to observe it. Ultimate questions: why existence? What is consciousness? Is reality objective or subjective? What existed before Big Bang? Do we have free will? What is time's nature? Why these physical laws might be meaningless as asked. Asking why existence might assume existence requires cause, but causation operates within existence and might not apply to existence itself. Asking what consciousness is might assume dualism when consciousness and matter are identical or complementary aspects of unified reality. Asking whether reality is objective or subjective might impose false dichotomy when reality is participatory, neither purely independent nor purely mental. These questions might rest on faulty assumptions, use inadequate concepts, or address phenomena transcending language's expressive capacity. Like asking what color prime numbers have or where yesterday went, ultimate questions might be category errors, revealing language and thoughts limits rather than genuine puzzles awaiting answers. Recognizing limits to comprehension is itself profound insight. Reality might transcend human comprehension not through mystical obscurantism, but through cognitive limitations and conceptual frameworks' inherent constraints. Human cognition evolved for survival in ancestral environments, recognizing faces, tracking trajectories, understanding social dynamics, planning short-term actions. Our brains are not general truth-discovering engines, but specialized survival tools. Mathematical physics and scientific method vastly extend our understanding beyond evolutionary preparation, but fundamental limits remain. We think in time, space, and causation. These might be parochial features of our cognitive architecture, rather than reality's deep structure. Quantum mechanics reveals nature at small scales operates non-intuitively, violating common sense. Perhaps reality at its foundations operates in ways we cannot intuitively grasp, even with mathematical formalism. The edge of reality might be defined not by what exists, but by what our minds can conceptualize, making the ultimate boundary between reality and comprehension, rather than between existence and non-existence. embracing the mystery. Socratic wisdom, captured in the phrase, "I know that I know nothing," recognizes true knowledge begins with acknowledging ignorance's extent. Socrates understood that claiming knowledge without questioning assumptions leads to false certainty. The wisest person is not the one claiming most knowledge, but the one recognizing how little can be known with certainty. This applies profoundly to reality's nature. We construct models, theories, and beliefs about existence, but fundamental questions remain unanswered and perhaps unanswerable. Quantum mechanics works remarkably well for predictions, yet leaves interpretation questions unresolved after a century. Consciousness produces our entire experienced reality, yet remains scientifically mysterious. The universe's origin, fate, and extent exceed empirical reach. Recognizing these knowledge limits is not defeatism, but intellectual honesty, acknowledging that confidence should be proportional to evidence, and that many fundamental questions lack sufficient evidence for confident answers. Science reveals ever deeper mysteries, rather than progressing toward complete understanding. Each answered question spawns new questions. Each discovery reveals new unknowns. Newton explained planetary motion, but couldn't explain gravity's cause. Einstein did with space-time curvature. But curved space-time raises questions about quantum gravity. We discovered atoms, then subatomic particles, then quarks and leptons, now questioning whether strings or other structures are more fundamental. The observable universe expanded from visible stars to billions of galaxies across 93 billion light-years. Now we ask what lies beyond horizon and whether multiverses exist. Consciousness emerges from billions of neurons firing. But why does this produce subjective experience? Dark matter comprises 85% of matter. Dark energy 68% of total density. We don't know what constitutes 95% of the universe. Scientific progress illuminates specific questions, while revealing vaster darkness beyond, suggesting complete understanding perpetually recedes before us, like horizon. Limits of knowledge don't diminish wonder, but deepen it. Mystery invites exploration, questions drive discovery, unknowns inspire awe. If everything were known and understood, existence would be a sterile catalogue of facts. But reality exceeds our grasp. Quantum superposition defies classical logic. Consciousness emerges from matter mysteriously. Space-time warps and curves. Time dilates and simultaneity becomes relative. Particles tunnel through barriers. Energy fluctuates in vacuum. Black holes radiate and evaporate. The universe accelerates in expansion, driven by unknown dark energy. Each phenomenon challenges intuition and comprehension. The edge of reality, where knowledge meets mystery, is where wonder flourishes, where we confront existence's profound strangeness and recognize our place as finite minds contemplating infinite cosmos. Mystery is not enemy of knowledge, but its complement, providing direction for investigation and humility about claims' scope. Reality as participation rather than passive observation reflects quantum mechanics' lesson that observer and observed are entangled. Measurement affects outcomes. Consciousness might collapse wave functions. We don't stand outside reality, examining it objectively. We're embedded within reality, participating in its unfolding through observation and action. Wheeler's participatory universe suggests observers co-create reality through observation. Many worlds' interpretation suggests we navigate branching possibilities through choices. Even classical physics shows observer dependence through reference frame relativity. No privileged perspective exists from which objective reality is revealed. Participation means reality is process rather than static object, dynamic rather than predetermined, interactive rather than separate from consciousness. This shifts perspective from seeking objective truth independent of observers to understanding reality as emerging through observer participatory engagement, where subject and object merge at the edge. Subjective and objective reality are intertwined rather than separate domains. Subjective experience is undeniably real consciousness. Qualia, feelings, thoughts exist as immediate first-person facts, more certain than any third-person observation. Yet subjective experience correlates with objective brain states. Manipulating neurons affects consciousness. Brain damage alters experience. Objective physical reality apparently exists. Consistent mathematical laws, reproducible experiments, successful predictions suggest reality transcends individual minds. Yet quantum mechanics shows observation affects physical outcomes, and we access objective reality only through subjective experience. Perhaps reality has irreducibly both aspects inside and outside, first person and third person, mental and physical as complementary perspectives on unified existence. The edge between subjective and objective might be permeable boundary rather than absolute division, with consciousness and matter being aspects of neutral monism, where neither is fundamental alone, but both emerge from deeper reality, meaning created through conscious experience rather than inherent in objective universe, reflects existentialist insight that existence precedes essence. We exist first, then create meaning through choices and experiences. The universe displays no inherent purpose visible to science. Galaxies form, stars burn, planets orbit following physical law without apparent goal. Yet conscious beings create meaning through relationships, achievements, creative works, understanding, love, suffering, growth. Meaning is subjective but not arbitrary. It arises from values, commitments, and engagement with existence. The edge of reality includes this meaning creation process, where consciousness transforms physical existence into meaningful experience. Even if the universe is simulation, meaning we create within it remains real to us. Even if we're quantum fluctuations, our experiences matter to ourselves. Meaning is generated internally through participation in existence, rather than discovered externally in objective facts. Mystery invites exploration rather than despair. Unknowns drive discovery rather than paralyze investigation. Science flourished precisely by acknowledging ignorance and systematically exploring mysteries. The scientific method is process for converting mystery into understanding through observation, hypothesis, testing, and revision. But some mysteries might be permanent hard problem of consciousness, origin of existence, nature of time, quantum measurement problem, reconciling quantum mechanics and gravity. These resistant mysteries don't mean abandon inquiry, but suggest humble engagement where we acknowledge limits while pushing boundaries. Mystery keeps reality open and dynamic rather than closed and complete. If reality were fully known, no discoveries remained possible, no growth occurred. Mystery is not failure, but opportunity. Not ignorance to be ashamed of, but frontier inviting exploration. Not edge marking understanding's end, but boundary revealing existence's depth. The unknowable edge keeps reality open and dynamic by preventing complete deterministic closure. If everything were knowable in principle, reality would be deterministic, clockwork given complete information about present. All future states are predetermined. But quantum randomness, consciousness's apparent freedom, Gödelian incompleteness, and observational horizons create fundamental openness. The future is not uniquely determined by the past. Quantum measurement produces genuinely random outcomes. Consciousness might introduce novel causes, mathematical truth exceeds provability, and beyond horizon, reality evolves independently. This openness allows novelty, creativity, free will, and genuine becoming rather than mere unfolding of predetermined script. The edge where knowledge meets unknowable is where possibility exists, where the future is genuinely undetermined, where consciousness participates in creating rather than merely observing reality. Embracing mystery means accepting this openness as feature rather than bug of existence, the journey's end and new beginning. The journey beyond reality's edge has traversed perception's limits, showing human senses access tiny fraction of electromagnetic spectrum, while other species perceive different slices of existence. Quantum measurement problems, revealing observation, affects outcomes, and reality depends on measurement context. Heisenberg uncertainty demonstrating fundamental limits to knowledge where complementary properties cannot be simultaneously known. Observer effects suggesting consciousness might collapse quantum possibilities into definite outcomes. Extra dimensions proposing reality has more spatial dimensions than accessible to perception. Holographic principles indicating three-dimensional space might be projection from two-dimensional information, and simulation hypotheses questioning whether we exist in computational substrate. We've explored particle horizons bounding the observable universe at 93 billion light-years, black hole event horizons where information appears lost and space-time itself becomes uncertain, and 4 levels of multiverse, from infinite space to eternal inflation to quantum many-worlds to all mathematical structures existing equally. We've considered block universe, where time is dimension like space making past and future equally real. Consciousness possibly transcending physical brain substrate. Nested simulations creating infinite hierarchies where base reality might be unreachable or non-existent. Conscious reality creation through observation retroactively determining past, and the unknowable aspects of reality exceeding human comprehension. The edge of reality reveals reality's profound strangeness. Nothing is as it seems from naive experience. Common sense breaks down thoroughly at reality's foundations. Space is not passive container, but dynamic fabric warping and curving. Time is not universal, but relative depending on motion and gravity. Matter is not solid, but mostly empty space, with particles themselves being quantum waves of possibility. Causation is not deterministic, but probabilistic, with quantum randomness pervading nature. Consciousness is not explained by anything material, yet correlates perfectly with brain states. Observation affects outcomes violating classical assumptions about observer-independent reality. Multiple realities might exist in parallel through quantum branching. We might be simulated beings in computational substrate. The universe might be holographic projection from lower dimensional boundary. Everything might be mathematics existing necessarily without physical instantiation. These aren't science fiction speculations, but serious proposals from physics, supported by equations, experiments, and observations. Reality at its edge is far stranger than imagination alone would produce. The mystery at reality's edge invites ongoing exploration, despite or because of fundamental unknowns. Science continues pushing boundaries, quantum gravity theories, attempting to unify quantum mechanics and relativity, consciousness research seeking neural correlates and attempting to explain subjective experience, cosmological observations mapping universe's structure and evolution, particle accelerators probing higher energies, quantum computers exploring computational possibilities, neuroscience mapping brain connectivity and function, artificial intelligence perhaps creating synthetic consciousness. Each advance reveals new questions, new mysteries, new edges. The journey beyond reality's edge has no final destination, because reality continuously transcends our grasp. But this doesn't counsel resignation. It means exploration continues indefinitely, each generation pushing understanding further while recognizing limits. The edge recedes before us, but the journey itself provides meaning through wonder, discovery, understanding, and participation in existence's unfolding mystery. Humility about knowledge claims emerges naturally from recognizing how much remains unknown and perhaps unknowable. Certainty should be proportional to evidence. Quantum mechanics predictions deserve high confidence because experimentally confirmed to extraordinary precision. Consciousness causes wave function collapse deserves low confidence because speculative without empirical support. We're in simulation deserves suspension of judgment because unfalsifiable. Intellectual humility means holding beliefs tentatively, revising them when evidence changes, acknowledging ignorance gracefully, and avoiding dogmatism about fundamental questions that exceed current knowledge. This applies to scientific materialists claiming consciousness will be explained purely physically, idealists claiming matter is derivative from mind, theists claiming God necessarily exists, atheists claiming God necessarily doesn't exist, and anyone claiming certainty about ultimate reality's nature. Humility means acknowledging we're finite minds with limited sensory access, evolved for survival rather than truth, attempting to understand existence from impossibly narrow perspective. The participatory nature of reality means we're not separate from what we study. Observer and observed are entangled in physics, subject and object merge in consciousness, knower and known interpenetrate in experience. This collapses Cartesian divide between res cogitans and res extensa, mind and matter, subject and object. Reality is not spectacle we watch from outside, but process we co-create through participation. Quantum observation affects outcomes. Consciousness experiences itself through reflective awareness, and understanding changes what is understood by revealing new aspects and possibilities. The edge of reality is participatory boundary, where we engage existence rather than passive limit, where observation ends. This suggests reality is fundamentally relational and interactive, rather than composed of separate independent objects. We don't discover pre-existing objective truth, but participate in truth's emergence through engagement with existence. Meaning and purpose are created through engagement with mystery, rather than found in objective facts. The universe displays no inherent meaning accessible to physics, it simply exists, evolving according to mathematical laws without apparent goal. Yet conscious beings create meaning through relationships, values, understanding, creative expression, moral commitment, and participation in communities. This meaning is real. Despite being subjectively generated, it shapes experience profoundly and determines what matters to us. The edge of reality includes this meaning creation capacity as essential feature of conscious existence. Even if we're simulations, patterns in quantum fields, or temporary structures in block universe, the meaning we create within our experience remains authentic and valuable. Embracing mystery means accepting that objective universe provides no answers to meaning questions, while recognizing we generate meaning through how we engage existence's mysteries. The journey beyond reality's edge ultimately reveals that edges are fuzzy boundaries rather than sharp limits, thresholds inviting further exploration rather than walls forbidding progress, interfaces where knowledge meets mystery rather than absolute endpoints where understanding terminates. We've encountered edges between observable and unobservable at particle horizons, between knowable and unknowable at quantum uncertainty, between conscious and unconscious at awareness boundaries, between real and simulated at computational substrates, between subjective and objective where observer meets observed, between provable and true at Gödelian limits, between comprehensible and incomprehensible where concepts fail. These edges define our epistemic situation. We exist at boundaries, inhabiting interface between finite knowing and infinite unknown, participating in reality while remaining irreducibly mysterious to ourselves. The edge of reality is not where reality ends, but where our understanding reaches its current limits, inviting perpetual journey into ever-receding mystery, where wonder, curiosity, and participation replace certainty, completion, and observation. This is not failure, but blessing reality exceeds our grasp infinitely, ensuring the journey continues forever with new discoveries, deeper mysteries, and enduring wonder at existence itself.